In this lecture, we will introduce the field of data mining, and we will be talking about various aspects related to digital data. Over the last few decades, we have seen that there is a rapid growth of information represented in some digital form, and we generally refer to it as to data. The data has grown to such extent that we see over already quite some time that there is a shift of traditional sciences and approaches. For example, in the past, it was common that scientists would have a particular hypothesis, and based on that hypothesis, they would be starting to collect data to either support that hypothesis or reject it. Now, at this point, the data collection is not directly considered for confirming or rejecting the hypothesis. The data is being collected literally wherever possible, and it might be evaluated at some later point in time, and it might be leading to some new insights or to hypothesis formation. So in fact, the data itself will be at the beginning of also scientific discoveries, where the data hypothesis formation will be a direct consequence of analysis of certain data. So there is a new mantra of gathering data, whatever data and wherever and whenever possible, so that we have as much data as possible, and we can then perform analysis so that we understand what this data represents. This is done in many fields, and we expect that the data will have a value either for the purpose it was collected, or it will have a value for a purpose which is not envisioned at the time of data collection. This is done both in academia and also in industry and various other social institutions and departments, such as medical departments and so on. And we can see that in case of big companies, a lot of data is collected and warehoused at Google, Facebook, Amazon, but also in various financial institutions, so that we understand how credit card transactions work. And this brings a lot of advantage to these companies, because people say that data is currently the new currency. And for example, Google would have information about a lot of the users of the Google services. Facebook will have, or Meta, a lot of information about users who use their social networks. Amazon will have a lot of data from customers who are buying various products, and credit card holders will be providing information to Visa or MasterCard or their banks about their transactions. And in many cases, this will be the data they are providing, and collectively many users, this will lead to some advantage. For example, you can now use various services such as translations or auto completion of text, or formulation of text based on prompt, based on all these inputs, which based on all this data, which, for example, Google has and is using it in its Gemini. Similarly, if you perform various purchases, you have a certain profile at your financial institution, and if suddenly there is a transaction which violates your routine purchase profile, the bank will be alerted and will perhaps block your card, because your purchase has been suspicious, that it is not actually issued by yourself. And this is definitely of benefit to the end user. And this is essentially a result of data analysis and data mining workflows. So, based on this understanding of data, industrial companies are seeing that they get a competitive advantage if they understand the data properly and if they can recommend you, for example, to buy a certain product based on your previous profile and profiles of others, they might gain you as a future customer because of this high quality service they are providing. In the case of sciences, the data mining helps scientists in automated analysis of massively large data sets and in hypothesis formation. Data mining can be considered as a non-trivial extraction of implicit, previously unknown, and potentially useful information from data. The stress is on non-trivial extraction because it includes a lot of data sets. It includes a lot of methods which are able to handle data which is in form which is not trivial to handle. For example, the data can be very large, or the data can be heterogeneous, or the data can be very complex otherwise, and or distributed at various locations, not at one place. All these are complex representations of data or aspects of data, which might lead to the fact that simple information extraction methods are not possible to perform, and it will be dedicated algorithms will be necessary. So data mining is a set of exploration and analysis techniques which are either fully automated or semi-automatic, and it is these data mining techniques are able to handle large quantities of data in order to discover meaningful patterns. We can see the data mining kind of originally being placed in a pipeline of knowledge discovery from databases, the KDD, which was is a research field on its own, but the data mining plays such a central part that basically this entire pipeline is now considered could be considered as the data mining pipeline, where at the beginning we have some input data which we will talk about and characterize in the next. Then we have a lot of various pre-processing techniques such as feature selection, dimensionality reduction, normalization, data subsetting, and so on. And then after this pre-processing, we have various algorithms to perform the data mining, and we will see which type of algorithms these are. And after we have our data mining completed, we can show the result in various ways. We can either filter the information according to certain patterns. We can visualize the outcome of the data mining and aid the interpretation of patterns which were extracted from the data. So in general, we can be talking in data mining in about two methodologies. One methodology is related to prediction methods, where we use some variables of the data to predict unknown or future values of other variables, or also of current variables when it comes to future variables, what that could be. And in this case, we have, for example, an example of classification. Classification means that based on the data characteristics, we can assign the object to certain classes. That means that, for example, we can assign various plants, for as an example here, to various subgroups. We have here actually a visualization of some data related to the iris flower dataset. This iris flower dataset we will be talking about also later. It is containing information about 3 species of iris flowers, and these 3 species have been measured in terms of the flower of petal length and petal width, and also of some other aspects of this plant, so more characteristics than that. And we can see that if we have 150 different items, 150 different flowers have been measured, and you can see that, for example, there is a kind of a group here, and then there is a kind of a group here and a group here. And in fact, we can see that all these individual elements are coming from the type Iris setosa. So actually, if our petal length is under 2.5 centimeters and the petal width is under 0.5 centimeters, then it is with quite high certainty the Iris setosa flower. And if we have very high values of the petal length and width, it is with high probability the Iris virginica. And somewhere in the middle, we can see that this is the versicolor iris flower species, and we can see it relatively clearly in this plot. Although it's not completely discontinuous, not completely separable here, but we see that most of the data points here are circular, indicating that they belong to that species. So this is actually a case of prediction methods which are called classification. Classification can be seen in many other examples, and we will be talking about classification in this course on later lectures. Then the next category will be regression. And that's a prediction method which, unlike in classification, which assigns data points or data elements, data objects into various discrete classes, the regression is a prediction method which gives us a continuous value. For example, it can give us value of an estimation of what will be the weather temperature tomorrow. And that will be maybe on a like continuous scale in Celsius temperature unit, and it might be therefore represented as a single continuous value or real value, which will be the outcome of this prediction. So that's the difference between classification and regression, but both belong to these prediction methods of data mining. You can see classification and regression also as a part of machine learning. So these two fields are definitely overlapping, but some of the classification methods are more known as being part of the data mining, and some of them are more known as the machine learning classification methods, and the same holds for regression. And then we have some other methods in data mining which are called description methods. So they are not really predicting some new values from the current data values, but they are describing the data in some way. So we can find human interpretable patterns in the data that describe the data. For example, we can have a clustering method. So, for example, clustering method could be that we have some data of documents, and each document is actually represented not as a continuous flow of sentences, but instead it is just represented by counting some important words. So there are the document is represented by just a set of words, and the amount of repetitions of this word indicate for us what is that document about. And then if we have such a representation with some numbers associated to particular words, for example, in the case of transactions and financials, we will find some terminology which relates to finances, such as budget or funding or capital, could be typical words in such a context. While if we have documents about from the medical context, we might see the word like diagnosis or pathology or various expertises of from medicine, such as ophthalmology or pediatry, etc. And if we will compare these two documents of these from these two examples, we will clearly see that their words and their word count is somehow focused in some other terminology, and therefore we will be able to, with data mining methods, to cluster them and see that there are clusters which are talking about some financial aspects, and then there are other documents which are talking about some medical aspects. Then we can see that other types of methods could be interesting. For example, anomaly detection. So we can see that on one hand, we have some kind of formation of clusters, like for example, we can see here very clearly pronounced clusters, or maybe a little bit more spread. But then there are some data points which are clearly not part of some cluster, and we would call them outliers from statistics, but they can also be somehow indicators of a certain anomaly. Like, for example, in the case of bank transactions, you can have suddenly a very unusual bank transactions, maybe in terms of the amount which is being withdrawn or used for a certain purchase, which has never been observed from that particular customer before. That might be considered as statistically as an outlier and might trigger some kind of detection of anomaly. And then third example is known from the association analysis, and we will be talking about association analysis, for example, when we good example are these market basket analysis, which are trying to understand a typical profile of purchases. So if you are going to a supermarket and you buy several items, then it somehow characterizes your profile as a customer. And maybe you are buying often a milk, and maybe you buy yogurt, and then you are also buying bread. And therefore, if you one day buy bread, maybe there is an indication that you are likely also to go and buy the milk and the yogurt. So this association analysis finds these patterns and can perform, for example, some recommendations. So these two big classes of description methods and prediction methods are forming us the two directions in the data mining algorithms. After we have defined the basic concepts or approaches, methods in data mining, it is time that we have a closer look at data and characterize data from all possible perspectives and aspects before we dive into the data exploration and specific data mining methods that work and operate on this data. So data can be regarded as a collection of data objects and their attributes. The word attributes has a meaning of various aspects related to these data objects. So it is a property or characteristic of an object, such if we have an object, a person, the attribute can be eye color. If we have sea as an object or various points in the sea where we measure, it could be a temperature, for example. So attribute, we have several names for this property, and we can call it also a variable, we can call it a field, characteristic, we often hear it being called dimension, or a feature. So these are all terms which are used in various fields, but they all relate to the same thing, namely characterization of an object according to some specific well-chosen aspects. And a collection of attributes together forms an object entity, which possesses and is fully characterized by these attributes given our current scope of study. Object which contains all these attributes or is characterized by these attributes is also known by other words like record, because we record the data point, and or a point, we can call it a case, a sample, an entity, or an instance. So there are many words which characterize these two essential distinctions where the data is characterized by the data elements, namely objects, and then the characterization of these objects, which we will call here as attributes. We can see it very well on this table here, where the table, two-dimensional table, is characterizing as objects. Objects are here in rows, and we can see we have 10 objects, and each object is assigned a unique ID. The ID itself is already an attribute. Then we have some other attributes which we can see here. So first attribute was a different number, and the other attribute is just yes, no, which is really like just a binary true or false or 0 and 1 characterization. Then we have here another attribute which is similar to the previous one where we have, but here we have only two categories, either yes or no. This is a categorical variable where we have more possibilities. Marital status could be single, married, divorced, maybe widowed. And here we can see that the elements, namely the persons here, are characterized according to their marital status. Here we have yet another attribute, which is actually in, we can see either in integer numbers or in floating point numbers. Hard to say from here because this would be all integer numbers, but we can see that this characterizes more either this is not a categorical variable or attribute. This is more like a continuous one. And then we have again some kind of binary variable here, which is telling us how the person is financially doing. So you can see here, and on this very simple table, already a large variety of attributes and which characterize these particular objects. We will be dealing with this kind of characterization for a long time in this chapter, and we will be analyzing the various aspects of attributes and objects which are relevant for the pre-processing of data mining techniques. So first of all, the attribute is a certain characterization, maybe an age, you could say, or a temperature. That's an attribute. But it can be assigned different attribute values. So attribute is one thing, attribute values is another thing. Attribute can be age, attribute value will be just a integer number. Attribute values could be numbers, or it could be symbols assigned to an attribute for a particular object. By symbols, we mean there could be a symbol for gender, for example, or there could be a symbol for other characterization, like, for example, participation to a certain category, like, for example, animals versus flora or other types. Then actually the same attribute, let's say temperature, or here we have the height, can be mapped to a different attribute values. So height can be, for example, measured in feet or meters. So whether we are using the imperial units or the metric system. We can see here that both of them will be a continuous variable, continuous attribute. However, they will have simply different values. Feet measured in feet, we would typically be having larger numbers than if we are measured in meters. Not typically, always, because the feet itself is a smaller measure of length than a meter is. Then we have different attributes can be mapped to the same set of values. Like, for example, we could have very different attributes like an ID or an age, and both will be integers. While for the ID, it would not make sense to sum up or subtract certain IDs from each other. For age, this might not be irrelevant. If we want to compare how much older one person is from another one, we would simply perform this simple arithmetic operation of difference to find that out. If we will subtract two IDs, we will not be able to find out anything except if they would be that would be the same ID and would give us the zero. That would mean that the ID was twice the same and it's twice the same person. So we could use various types of values for a completely, or the same type of values for completely different purpose. So properties of an attribute can be different than the properties of values used to represent an attribute, meaning that even if we can, in case of integer values, can subtract or maybe multiply the values by some constant, that would not really make much sense to an ID attribute, while it might make sense for an age. And therefore, it is always important to consider in which context are we using the particular type of values. We can categorize attributes into four basic types. And these are the following: nominal type, ordinal, interval, and ratio. So when we say nominal type, this really means that this is just a categorical variable where we have ID numbers, eye color, zip codes, gender, or other categories. So there is no reason for comparing these by their by certain magnitude, we cannot compare the green color, whether it is bigger or smaller than the blue color. And the same doesn't really make sense to do about the zip codes or about the ID numbers. There could be always exceptions. For example, if the ID numbers are always issued in the way that the oldest employees have the lowest values for the ID numbers, that could be then make sense to compare them, and by that assume who has been working in the institution for a longer time. However, this is generally not the case, and even if that would be the case, it would no longer be a nominal variable. It would become an ordinal variable. An ordinal variable is a variable where we have certain rankings. We can express it by numerical values, which in the case of nominal variables, we do not have to. Blue color can be represented just by a blue, or eye color can be represented just by a colored square of the corresponding eye color as a symbol or the like. But for the ordinal variables, we will typically already use some kind of rankings which might be expressed mostly by numbers. However, we can also express it by some pictograms, by some symbols which would be sort of maybe growing in size or something like that. And by ordinal values, we can, for example, have like we can order the different values of the attribute, like for example, pain levels on a scale from 1 to 10, or technological readiness values would be also scaled on this level. We can, for example, have grades, which would be also ordinal values, or we can also represent height in the ordinal form, so not in really a more precise, exact, continuous representation, but rather just in kind of three categories which can be sorted, like a tall, medium, or short. So for this type of variables, we have slightly different possibilities. What can we do with them? Then, for example, with at the next category, which are the interval variables, which is already now a more of a numerical property, numerical attribute, like for example calendar dates or temperatures, which would be continuous values. However, in this case, we have still not cannot fully use a mathematical machine or mathematical machinery here, because, for example, it doesn't really make much sense to talk about whether a Celsius temperature of 5 degrees is twice as or half as warm as the Celsius temperature of 10 degrees, because the zero in the Celsius scale is set arbitrary to the temperature of melting ice, which has been chosen for some specific reasons to be convenient for human, but it is not allowing us to do various operations for which other continuous variables we can use on. And the same holds for Fahrenheit, for example. We can see that right away that then we have the continuous variables which are of type ratio, which is, for example, temperature, but in Kelvin. We know that Kelvin is an absolute temperature. It doesn't have negative values like, for example, Celsius or Fahrenheit has. So Kelvin starts from 0, which is the absolute 0, where the molecules are simply not performing any Brownian motion. The movement is completely stopped, and this is not really achievable even in on on our planet to get to complete 0, but we can get reasonably close to that number. Anyways, we can have with temperature in Kelvin, we can, for example, say that temperature of 200 Kelvin is half of a temperature of Kelvin value of 400. Another typical attribute could be length, which is using ratio attribute values, counts, elapsed time of something, some process, or time to run a race, which starts from a certain 0 and then is monotonically increasing. We can see here different aspects of the difference between, for example, ordinal values here and the interval values here, or maybe actually also ratio, where on the right-hand side is something what we would expect, where we have these various sticks, and we can say that A is half the length of the B, and the C is 3 times the length of A, and the D is 4 times, and the E is 5 times, and it is all corresponds. So this is actually the ratio type of continuous variable, or actually it could be also an integer variable, where all these holds. Now, on the other side, on the left side, we have some weird numbers, which we would find that they do not really fit. But on the other hand, imagine that we have simply sorting of people according to a certain height, and they will be given some kind of order. And now we take the 5th person, 7th person, 8th person, 10th person, and 15th person. This will be their respective heights. I mean, these heights are very different in this particular example. So this person would be much taller than this person, which is unrealistic. But let's, for the sake of this example, imagine that we have elements of something, maybe a wooden logs, which have been sorted, and then we take just their value after they have been sorted. They have been no longer just like an ID number, but they have been of ordinal value, as I already explained before. So, and then what we can see that 5 is smaller than 7, 7 is smaller than 8, but we do not actually have the ratio between those. We cannot really say based on these values the what is exactly their relationship. We can only say that 10 is bigger than 8, 8 is bigger than 7, 7 is bigger than 5, but how much, this we cannot tell. So what type of operation can we apply to these different types of attribute values? So if the property is simply categorical value, we can only just compare them, whether they are the same or not the same. If there is no order, there is not much more we can talk about. If there is an order, like for example, the sorted enumeration of wooden logs, for example, we can say whether a wooden log is shorter or longer based on their order within the given sorting. If we have then also some interval values, then we can also talk about the differences, whether they are meaningful. Like for example, we can have we can talk about the age. That could be one variable or attribute by integer numbers where such a difference will be meaningful. If we are talking again about the temperatures, like the Celsius or Fahrenheit, it might make sense to increase the temperature by 1 degree and we can expect that it will change something in the temperature. So these arithmetic operations would make sense there. Then for the ratios, what is meaningful additionally are the operations of multiplication and division, so that we can say that something is twice as the quantity, like for example the length. So for nominal attribute, we have only the distinctness. For ordinal attribute, we have distinctness and order, so these two. Then for interval attribute, we have distinctness, order, meaningful differences. And for ratio attribute, we have also all the 4 properties. So as an example, which I already gave, difference between the interval and ratio type of attributes is that whether it is physically meaningful to say the temperature of 10 degrees is twice of Celsius is twice of 5 on Celsius scale, or on Kelvin scale. For one, it is physically meaningful, on the other one, it is not. Here we have a table which summarizes these 4 categorical, these 4 types of attributes: nominal, ordinal, interval, and ratio, where the first 2 are categorical or qualitative, and the other 2 are numeric or quantitative attributes, where we can, in the second column, see what type of relationships we can see between them, like, for example, whether they are equal or not. In the ordinal case, whether they are bigger or smaller. In the case of interval, we can perform some express some meaningful differences, or in the case of ratio, we can see whether something is x times the value of another of the same attribute. So here we have the examples of these 4. For the nominal, we have zip codes, employee, ID numbers, eye color, gender. I will now continue describing the row so that we can see that with these examples, what makes sense to perform some kind of operations on that could be to find the mode, entropy, contingency correlation, or the chi-square test. Some of these operations we will be describing as a part of this lecture. Some of these will be just kept here as examples. If we want to perform some transformation of maybe employee ID numbers, actually any permutation of values would be valid. Imagine that we have for each employee a 5-digit ID number, and now we just permute those 5 digits in a systematic way. So for each employee in the same way, let's say we maybe swap the first and the last digit of our 5-digit ID number. This will be completely fine. There will be no problem with using these ID numbers if they were not sorted before in any way, and if they have been issued in a random order. So that is, for example, a transformation which can be applied on this type of categorical attribute type. So if all employee numbers were reassigned, would it make any difference? If they would be reassigned in a completely systematic way, this would not make any difference. So for ordinal values, what makes sense to use them for is, for example, for hardness of minerals, when we are looking for a certain quality of diamonds, for example, maybe as or characterization of quality, whether something is good, better, or best, whether in terms of grades or street numbers. This all makes sense as we know that there are often streets where there would be maybe some numbers starting and ending at different values. There could be some number missing for some reason, and so on. So that would therefore count into the ordinal type. What we can do with ordinal types of attributes is that we can find a median value, we can find percentiles, rank correlation, rounds tests, or sign tests. So, and again, we will be talking about some of this operation in the next. The order, the transformation which can be done can be any transformation that preserves that order. So, for example, if we have a certain value associated with each of these hardness of minerals, like for example 1, 2, and 3, where 1 is the worst and 2 is middle and 3 is the best, we can also change it to 0, 1, and 2. Or we can also change it to -1, 0, and 1. And there will be practically no change in this usage of this qualitative attribute type. So if an attribute is encompassing the notion of good, better, and best, it can be represented equally well by the values 1, 2, 3, or also by 0.5, 1, and 10. That cannot be said the same for the quantitative attribute types like intervals, where the examples are the calendar dates or the temperatures in Celsius and Fahrenheit. Here we can not only calculate like median and the percentiles, which we can do here too, but we can also compute the mean, standard deviation, Peirce's correlation, or the various tests like the t-test or the f-test, which are characterizing us the various aspects related to the mean and the standard deviation or variance. The transformation of this interval can be done in a way that we have some a and b, which would be some numerical constants, and the new value will be simply a multiplication of the old value plus some addition, some bias term. And with this transformation, we will keep the same properties as we had with the old values. So that could be also seen how we can also perform actually transformation between the Fahrenheit and Celsius, as these scales are somehow computable based on this type of template formula. So the Fahrenheit and Celsius temperature scales differ in terms of where their zero value is and the size of the unit, and that could be compensated by this formula here. Then we have the last attribute type of quantitative nature, where we can also talk about the ratios, and this is temperature in Kelvin, monetary quantities, pounds, age, mass, length, current. So a lot of physical quantities can be used in this case. In addition to the previous statistical characterizations here, we can also use harmonic mean, geometric mean, percent variation to express their property of this attribute. If we want to change that attribute, we can just maybe perform scaling. Like, for example, we can measure the length in meters or feet, where 0 will still have the same meaning. So we cannot perform a change by adding here p, like p, where we were moving where the 0 was positioned. We cannot do that for the ratio where the 0 must be the same concept, even if we use different attribute value. Now that we have a good understanding of the qualitative and quantitative attributes, It's good to conclude with stating that the discrete attributes has only finite or countably infinite set of values, like for example zip codes or counts or in general of some items, and or the words in a collection of documents. So if we are counting words of a certain specific words in the document, that could be a discrete attribute. And then we can this can be represented as an integer or in a binary format, for example. Discrete integer can discrete attribute can be also represented by some symbols, as I said and indicated before. However, if this is a symbolic representation, it is maybe good for representing it visually, but maybe it is not good for its digital representation, where the numbers or binary values can be much more effectively represented. Then we have the continuous attribute, which is represented by, which is kind of encoding real numbers as attribute values like temperatures, height, or weight. And these continuous variables are like the continuity is there theoretically because the continuous attributes are representing as floating point variables, and even if they would be able to represent many numbers, they still have a finite precision. So what the intent is to represent continuous attributes with some kind of real numbers representation, but we cannot have a complete real numbers representation on the computer, and we will at the end of the day use a finite precision. But therefore we can use a different number of bits for representing this finite precision in order to satisfy a certain requirements of the underlying use case. Then we have something interesting, which is called an asymmetric attribute, which can be a binary or continuous attribute where a non-zero presence is regarded as important. Like, for example, imagine that we have some kind of roster of all students, and the attributes will be all courses which the students can choose at the university, like student table and all courses. So we can imagine a student of mechanical engineering will not be taking too many courses in philosophy or history, and there will be a lot of zeros because the student didn't take it for obvious reasons, and there will be only some value, for example, that the student took that course, may be represented by true or binary value of 1, that the student took the course in case of maybe mathematics or some fundamental engineering courses. So that means that this asymmetric attribute would result into a case where there will be a lot of zeros, and the zeros are typically not very informative, and only what is informative are the those attributes where there is 1 for that particular data object. It doesn't necessarily need to be only binary representation. You can imagine that in this student versus all university courses case, we can also have the grade. So it could be an attribute which will be a grade or 0, and the 0 would mean that the student didn't take that course. Now, we have discussed this aspect of data in the case of like looking at the attributes and the objects. But now we will have a look at the entire ensemble of this information in the form of the so-called data set. So it's not only like a data item or data attribute which we looked and dissected it into its properties, but let's have a look at characteristic of data sets. So in a data set, we can talk about the number of attributes or number of dimensions, if you like, and that will be characterizing the dimensionality of the data set. So if we have something of high dimensionality. That means we have a lot of attributes, and this becomes the naturally more challenging case than a low dimensional data set, which is perhaps easier to handle, more practical, and for data mining purposes, sometimes even so easy to handle of low dimensional data that we do not really need to have any advanced algorithms applied. However, high-dimensional data can be very challenging if we have thousands of attributes, 10,000s of attributes that will become a complicated case. And we will be talking about various aspects there. Like, for example, the curse of dimensionality is something which is coming naturally with increased number of dimensions or attributes we are having in our data sets. Therefore, it is important that if we have a particular situation and particular scope of analysis, it would be good to exclude certain attributes which are currently not relevant for that particular scope. The sparsity of a data set, like in asymmetric features, might lead that only 1% of the entries are non-zero. So that could, on one hand, complicate the situation, because we need to maybe expand that information at some point in time. But it could be also beneficial because a seemingly large data set could be actually represented in such a way, maybe compressed, so that the data size to process and store will become smaller. So the sparsity can be both good and bad. The resolution of a data set tells us something about what is the specific level of detail that is characterizing the particular aspect. So imagine that we have just a simple image, and this image is representing us a photo of let's say a person's face, and if we have a resolution, meaning too few pixels, like let's say just 100 of pixels, then we might not see too much of a detail of a person, and we might not be able to recognize that person just based on information coming from 100 pixels. However, if we have information of 1 million pixels, that would be probably enough detail to distinguish one person from another person. On the other hand, the information, sometimes higher resolution, might be kind of misleading if we are into, let's say, if we are looking at the satellite imagery, and I would like to find out whether a part of land which is being currently viewed is a let's say urban area, whether it is a forested area or it is a area of a farmland, then at specific level of scale, these different areas could be very well distinguishable. However, at some other level, we might, which is the more detailed, we might actually see more details, but the actual characterization might be more tricky. So, for example, for forestry, if we are looking at summer satellite imagery, we can just take all the green values as the forests. However, if we are on a specific level of detail of a city, we might then erroneously also assign gardens to be forests or small parks to become of a forest type, which would be in principle not a correct assignment, because those are not large forest areas of green zone. Similarly, gardens could be then represented as farmlands, which would also not be very correct. That could also be similarly seen in, for example, the X-ray images. In X-ray images, it is relatively easy to see whether something is a bone or it is a soft tissue. However, if we will have a very high resolution of the X-ray imagery to the level of cells, then the cells will actually make this distinction between the bone tissue and the actual soft tissue harder to carry out. So sometimes high resolution might be good, sometimes a lower resolution might perform a certain task easier. Let's discuss what types of datasets do we have. We have been discussing so far the in most cases the so-called record dataset, where we have an assortment of various records. Like for example, we can see on the right-hand side, we have some various records here. Like for example, we could have the transaction data, where each record involves a set of items and can be represented as asymmetric attributes, for example, with binary, integer, or continuous values. So, for example, here we can see that we have some kind of transaction data. So there has been some purchases made, and this is somehow the transactions has a certain ID. And if we will have items like bread, soda, milk, we can have that each of these types as a separate attribute. And if there is a bread, then we will have the one there. And if the transaction there is no bread, like for example here, there will be for the bread attribute 0, but there will be 1 for beer or soda or diaper or milk. But for the other aspects, there will be 0. Then, so this is the one type of record. We will be typically talking about record data as a type of a data matrix. So data matrix means that we have just numbers, and the numbers are forming just like rows of objects and columns of attributes or dimensions. So this would be a typical data matrix case. Where we have a matrix of 1, 2, 3, 4, 1, 2, 3, 4, 5 columns. So 4 times 5 matrix. And with this matrix, we can already perform some interesting linear algebra operations, which could be leading to some information. For example, in case of dimensionality reduction, we can use the mathematical machinery here from understanding this huge matrix, what it actually kind of represents, where the most important attributes are. Then we can have the sparse data matrix, for example, which could be using these asymmetric attributes, which would be an efficient representation, for example, for transaction data or also for so-called document data, where we have the matrix of documents versus words. So imagine here we have a document 1, document 2, document 3, and in this case we can see that in the document 1 we are talking about the team, about the play, about the score, game, and loss, and season. So this is one type of document. All of these documents seem to be about sports. However, this second document is talking a lot about the coach, and there is some kind of a loss. Maybe there could be a relationship between these two most frequently appearing words in this document too, while in the case of the document 3, we are talking about the win of a game and not so much about the coach. However, we are talking quite about timeout, which might have been relevant for the case of a win of the game. So if there are carefully chosen words, those could characterize the document and give some kind of base for an analysis. A typical analysis in documents could be either the scope, what it is about, in terms of this frequency of numbers analysis, frequency of terms analysis, but also of things like sentiment analysis. So certain words are more associated with the happiness. Maybe some words are associated with some sadness or angriness or confusion. And those words, therefore, if they have occurred in high frequencies, they could give us a glance into the sentiment of the document, whether it has been a document which has been enthusiastic and positive, or whether it was rather a negative content in terms of various aspects that worry some people. In the record data, there might have been some relationships between the data elements, like, for example, if we have various transactions, some of these transactions could have been done by the same person. However, this is not an explicitly represented information there. And generally, we can often have relationships in our data, which can be expressed either implicitly or explicitly. And the graph-based data representation, which has this explicit linkage between the different objects, like for example here in this visualization, you can see that there are different classes. These are like school classes, and these school classes are representing as friendship networks. Friendship networks which are formed within the class between the different pupils, or also across different classes. So we can see that this friendship aspect is represented by an edge, and the individual data objects, the rows in our data matrix, will be the individual pupils. So here we have something which is there is a relationship, but it is not truly a physical relationship, in the sense that there is a kind of a physical connection between the two data objects. It's a relationship which is on a more abstract level, and we give this relationship a geometric representation, or generally a relationship representation. And this could represent something like social networks, as shown here, maybe knowledge graphs, or for example scene graphs, where the knowledge graph would be representing a relationship between, let's say, for example, a teacher is teaching in a class. So there is a relationship between the teacher and the class, and although it's not a physical bond, it might be a physical presence though of a teacher in the class. However, the knowledge graph will be capturing that by a link, or a edge, or an arc, as we used to call this kind of line connector between two objects. And then there is a scene graph, which is similar, but similarly characterizing the scene, a 3D scene, where we can say that there is a pen on the table, so there is or there is an painting near the chair, and these all can be represented by some relationships between the different objects. Then there are different objects which have these, which are represented as graphs with relationships, where this physical relationship between the different entities is kind of much more explicit. Like, for example, chemical structures that encode atoms as nodes and bonds as edges. So that means like bond is often represented by sharing an electron. One atom is sharing an electron with another atom, and that creates the bond. Or more atoms and more electrons, and that creates even a stronger bond. So this bonding through sharing electrons, that can be therefore representing an edge, as we can see here on this representation of some benzene core, where there are some, here there are of these carbon atoms, and they are sharing an electron with the hydrogen, and also they are sharing electron with other carbons, and therefore they are forming this together, this complex stable structure. There could be also more other explicit cases of graphs, like for example road network in countries between different cities, we can represent the roads by edges in a abstract graph of the cities, like we have seen in the previous cases when we were dealing with the search and the route planning scenario. So these are all types of data sets which use the relationship and are graph-based data where the relationship is made either an abstract relationship or it is a very concrete physical object itself which establishes the relationship between the other objects. The next type of data sets are data sets where the order of the data items of the data object have a certain meaning in sense of maybe of how they are occurring over time or some other relationship. So in case of order data, we can talk about the sequential data that can be or also called temporal data, maybe for transactions. Like we can see here, in this case, we have the temporal data where the transaction is following another transaction, and we can see these records. We can also then represent this table by some other reformatting, where we therefore have only few of the attributes, and we somehow merge the other attributes together. Like we can see a customer, which is then the object, and then we can see the individual transactions which he or she has conducted. Then there is another maybe type of order data, which is a sequence data. So not sequential, but sequence is ordered set of words or letters without a timestamp. Like for example here, we can see the certain genetic code. As you know, our genetic information is carried in the DNA macromolecule, which is stored in each nucleus of our cell, and each of the DNA is a very long set of nucleic acid elements, and these nucleotides can be of 4 types: G, T, C, and A, and they have a certain complementarity, like the G always binds with C and the T always binds with A. So this is guanine, the C is cytosine, this is thymine, and A is adenine. And all these nucleotides are stored in the DNA in this double helix, forming a certain order. And this order is not explicitly temporal. It is more spatial. However, when it is being read, it is read in certain temporal sequence. So this this G will be read either before or after this another G, depending on how the reading mechanism proceeds. So this is a sequence data, and then which has a certain ordering of either words or of letters, as it is the case of the genome sequence for genome sequence analysis. The time series data is a series of data points over time. And we can see, for example, here we have some kind of various data points over time. So here is several years from 82 to 94 of certain temperatures of Minneapolis. And we can see how these temperatures are changing over the year. Of course, we have a period of cold weather, and in Fahrenheit, I assume, and then, or maybe even in Celsius. And then we have here temperatures this will be definitely in Celsius. We have temperatures of high temperatures, and we can see how this cycle of seasons is evolving over this period of over 10 years. Then what we can see here is that there is a certain so-called temporal autocorrelation, meaning that if I look at a random element in this sequence, if I look at its predecessor or the point after, just next data point, their values will be approximately similar. They will not be very varying. While if I look at the a little bit more distant data point, the value can be quite different. So this is known as the temporal autocorrelation, where the neighbors of neighboring data entries will have roughly similar value. Then we have spatial data, which is also ordered data, but here, let's say the order is kind of in terms of the longitude and latitude coordinates in 2 dimensions. And this information stores information over geographic location, such as weather data, maybe salinity of oceans, or weather or temperature of the seas, or it could be data from engineering forming not a 2D representation, but a 3D mesh or grid. And in this case, we will be talking about the so-called spatial autocorrelation, where one point, let's say a salinity in a certain region here in the ocean, will have a very similar value to the salinity of a point, measurement point next to it. So then we are talking about the spatial autocorrelation, and in case we have like a spatio-temporal data, we could maybe have something like a spatio-temporal autocorrelation, where a point in space at the same at a slightly different time, the same point will have the similar value, or point which is nearby and at slightly different time could also have a very similar value. After we have characterized all these various types of aspects of data, data items, data attributes, types of data sets, we will have a look at what are the aspects of data quality. Data quality can be is characterizing the data after it is being measured and collected, and we can have certain types of quality characterization of it, like for example errors. So error in data affects the data quality, and it can be, for example, originating from the as a measurement error, where the measurement device is not very precise or it's not well calibrated, or we have a so-called data collection error, which is different from the measurement error in the sense that maybe we are we forgot to collect a point, maybe we are having some kind of statistical analysis of people living in a city, and we then forgot to visit one family, and then this data is absent from the entire data collection, and that will impact the data quality. So data mining often uses data that has been collected in the past, and even for a different purpose. Therefore, it is important to consider these various aspects of data quality. Typically, if we have measurements, the measurement devices get over time better. Like, for example, if we are looking at the MRI scans from 30 years ago, the data quality of MRI will be significantly worse than which is a common practice today. So therefore, the data quality should be considered, and if we are performing some longitudinal studies of MRI data, let's say of human brain, we need to understand that there is a different data quality 30 years ago than it is today. Therefore, the analytical pipeline should include some kind of specific data cleaning stage where the poor data is detected and somehow corrected. So, or somehow the data is put onto the same level in some sense. And the analytical pipeline should be based on algorithms that are robust and tolerate the poor data quality. So either we change the data, or we use algorithms that are robust to use data of different data quality. The typical errors in data typically originate either from the measurements, as I said, from the process of measurement, or from the data collection, where we omit objects or attributes or include data that should not have been included. Finally, it is important to mention that error can be either systematic or random. Like, for example, if we have a measurement device from the past, maybe the MRI, it will be systematically performing a lower resolution. However, if we have a device, even of today, there will be certain measurement noise which might be attributed to some background aspects, which is so noise is an omnipresent element in a random component of the measurement error. Like every time we measure something, there are some background aspects which are somehow contaminating this measurement. And like, for example, in case of MRI, if there is some kind of a magnetic presence in the room or nearby, maybe even elevator is moving up and down, this can influence the measurement of the MRI. Or if we have some other aspects as measurements from X-ray, we could have some other source of the X-rays or of the photons of that energy, which could be contaminating that error. That is like a random component. There could be also deterministic distortions, like, for example, streak in the same place of photos because the lens has been scratched. This is called an artifact. So, and we can also see such a more deterministic distortion in case of, let's say, the X-ray imaging, when we have, for example, some material which is highly absorbing the X-ray, and there is no transmission across that material, that could cause quite some measurement errors and distortions. So that would be called artifacts. These types of errors, noise, and artifacts are often associated with spatial and temporal data measurements. Because we typically, if we measure something, we measure it in a certain space which is relevant, the spatial location, or at a certain time which is also relevant. So it essentially eventually will be forming some kind of spatial or temporal or spatio-temporal data. For dealing with this kind of noise and artifacts, we can lean to signal processing methodologies, which can battle the noise to some degree and recover the signal. So, for example, we can perform some filtering of the data and smoothen the data, if you like, so that it will give less prominence to the noise. Like, for example, here we can see that we have a very noisy periodic signal, which is, but we can see that there is some kind of oscillation going on here. However, this oscillation is just having a has an additive noise. So always to a particular position in the period, we are adding or subtracting some random value on some kind of defined range, and that will give us this noisy looking sinusoid. However, if we perform some kind of a frequency analysis, at a certain periodic frequency, we can clearly recover a very strong signal. So a spectral analysis, for example, will recover the signal of this period, while there will be another smaller spikes of which will be related to periods which are would be then characterizing the noise. While those will be also present in the spectral analysis, their peaks will be much smaller than the dominant peak of the signal period. So that could be a way how we can handle that. However, it is not guaranteed that the signal processing will be able to completely separate the noise or artifacts from the signal, and therefore special care needs to be taken. Often, data mining focuses on robust algorithms that are less sensitive to noise. This is kind of inherited from statistics. There is a special robust statistics as they are called in statistics, which can be used, which are less sensitive to random variations. And we will be talking about that in the next. We can see, for example, here that while we have certain elements of points, we can see that these points of certain spatial measurement, if you like, could be contaminated by some noise which has been added here and which is kind of described here by these pluses here. So we can see how the noise was added to the otherwise noise-free signal. And one thing how we can battle a noise in general is to deal with repetition of a measurement. Imagine that we measure something several times, and always the measurement device will give us a slightly different value. Maybe we are putting something on a scale, and the scale has a certain capability of measuring that weight, and but it always comes a little bit different value. Then we can say that we can take these measurements and we can maybe perform an average of these values, and that could be considered the value which is the final one. This is very often used in physics experiments where we are characterizing then the maybe mean and then some kind of range from that mean where the measurement could characterize the true value of that quantity. So, but when we do these repeated measurements, we can also have a certain other characterizations which could be interesting. Like, for example, precision. Precision, if we perform a measurement, we can say that the measurement device is very precise, which doesn't mean that it is giving us the true value, but it just means that the repeated measurements are very close to each other. And that could be measured in range, or it could be measured in a standard deviation. So precision doesn't mean, could be the measurement device could be completely wrongly calibrated in some way, but and it will be systematically giving us a wrong answer, but these all wrong answers will be very close to each other, and that's where we will be able to say that the device is very precise. However, it might be giving us a completely wrong values. Another measure of repeated measurement or characterization is bias. That is actually exactly measuring what the precision is not measuring, and that is the systematic variation of measurements from the quantity being measured, meaning which is characterized by the difference of measurements of difference of measurements of mean from ground truth. So here, in case of bias, imagine that we are calculating not the standard deviation, which we will be talking about next, but we will be measuring the mean, the average value of all these measurements, and then we will be looking how far is this mean value far from the ground truth. Imagine that we know the ground truth of a certain quantity we are measuring, and then we can compare how much is the mean away from the ground truth that is characterizing as this bias. Ideally, the bias is zero. And then we have something which is called accuracy, which is another characterization of the repeated measurements, and that is the closest of measurements to the ground truth of quantity being measured, characterized as mean square error of measurements to the true value. So MSE measures the accuracy, which characterizes both the bias and precision in one measurement, in a way where we are having each measurement is then subtracted from the true value. The value of the measurement is subtracted from the true value. The difference is squared, and then the this is then squared and summed up together, and that will be the mean square error of measurements, which is characterizing then the accuracy and overall the quality of the measurement. Another aspect of data quality are outliers. In our data, we can often observe certain trends, like, for example, formation of certain clusters. Some clusters are very well pronounced, like this circle here. Some have a certain spread, maybe a little spread. Some have a little bit more spread. And then these could be called trends or clusters. And then we have some other phenomena in our data, which are called outliers. Those are data objects or attribute values with characteristics that are considerably different than the most of other data objects or attribute values in the dataset. So, and here we need to make a very important distinction. The outliers are legitimate data objects or values. They are not noise, but we can always have an outlier. Let's say in the school, we have a reasonably talented students who are pupils that can perform reasonably well in the courses, but we have one genius in the class who is performing just so much better in all courses which are, let's say, related to mathematics. So that person, she or he, will be an outlier in that context. The grades of that person will be significantly different than the grades of other students on average from the subject of mathematics. We can have many other outliers in terms of weather or other phenomena which we are studying. In every phenomenon or problem of study, we will probably, over real world, we will probably be experiencing some outliers. And those are important to be aware of, but sometimes we need to ignore them in order to, if we want to define trends. Outlier is definitely not setting a trend. Outlier is defying a trend, and if we are looking for trends, we need to make sure that the outliers are, for example, not impacting this analysis too much. So there could be contaminating analysis of trends, but at the same time, in other cases, they could be very, very relevant in anomaly characterization. So outliers are in principle anomaly. They are not the usual, the standard of the given phenomenon. They are an unusual manifestation. And here we can, for example, see the case of like fraud detection. If we will be just looking at trends and ignoring some transactions which are highly suspicious, we will not be able to detect fraud. If we focus on the outliers from transactions which are unusual from a certain aspect, we can be able to detect that anomaly. And therefore, anomaly detection is definitely very much focused on studying outliers. Another aspect of data quality, which is somehow orthogonal to the question of noise, is missing values. So sometimes values can be missing as a subject or reason behind it could be some kind of data collection error, and some values have not been measured. Or we can have in data some values which not always is possible to measure. For example, if you are asking some people what is their age or their weight, they might be hesitant to tell, and therefore these statistics might not be recorded because people simply refuse to share that information with the person who is performing the data collection. And then we will have missing value. What can we do then? Well, we can, if we have missing values, but just only very few data objects, let's say we have 10,000 people and only 3 objects or persons have refused to tell their weight, we can perhaps eliminate these data objects, these persons, from the overall statistics we are performing when we are studying the the typical proportions of people over a certain age or so. But if we have, we can also eliminate attributes of that kind if they are not so important for a given study. However, sometimes we do have a problem that eliminating would mean that a lot of data is being lost or ignored, and that would not be good. But sometimes it is possible to relatively easily estimate those missing values, and we can give these data objects with missing values for certain attributes some estimations of their values, and that could be then used in the statistics. So, or we can ignore that there is a missing value in the analysis, which could be sometimes suitable. Sometimes it might lead to heavy contamination of very wrong values in the analysis and should be avoided. There could be some inconsistent values, so not missing values, but inconsistent values. For example, if you have certain IDs in certain countries, that ID needs to sort of conform to a certain checksum. So if you sum up all those numbers in the ID, they need to be in some kind of range. They need to adhere some kind of rule, and maybe in some cases, this is not the case. So the ID number is guaranteedly wrong. We just don't know exactly how wrong it is, but maybe we can, based on this checksum principle, we can figure out where the mistake has been made. Perhaps a simple permutation of 2 digits in the ID could lead to a valid number, and that could be then fixing the given problem. Another aspect could be maybe a missing prefix. Imagine that we have a telephone number of somebody, but we do not really know what is the country of his cell phone number. Maybe by estimating, we can estimate it by knowing the nationality of that person, that that person might have the number related with the prefix of that country, and that could fix us the value. But it's an estimation, it's not for sure, but it's maybe a reasonable assumption. Sometimes we have duplicate data where the same data point is twice in the database. Like, for example, imagine that we are performing a collection of homeowners or people registered at a certain address, and then we have a certain person who has recently moved from one address to another, has registered the new address, but did not yet unregister the previous one. So that person will then appear in our database twice, always with a different address registered to that person. And it's a question: what should we deal? How should we deal with this kind of case? Sometimes we can delete an entry. Maybe that's a valid approach in some cases, but sometimes this is not a valid approach and would need a more careful handling. So if we have data of certain characteristics, let's say they have a certain level of noise, or we have a certain missing information, or the data is too big, there are certain aspects of the data which the data mining algorithm will be challenged with. We might perform so-called data preprocessing. And there are several data preprocessing steps we will be talking about, which can cope with some of the aspects which make the data especially challenging. Like, for example, the information of about the measurements. When the measurements are noisy, imagine that we have a lot of measurements of the same objects, and then we simply perform and find out an aggregate value, maybe an average. The average will be aggregate value, which will be probably a good estimate of the true value of that measurement. So aggregation can solve the problem of random noise, for example, But also, we can have the aggregation as a means to reduce a certain data size. Imagine that we have a two or more objects in the data, and we are then representing it as a single object. For example, we can represent a store transactions, so financial transactions from individual ones into one big single daily transaction. So where all the products which have been sold will be put together as one single transaction, and then we will, in case we are dealing with, let's say, 10 years of transactions, maybe an individual transactions will make the analysis infeasible, but if we aggregate it into daily transactions, suddenly the problem will be again tractable. We can calculate the sum when it makes sense to calculate the sum of transactions, for example. Sometimes we can calculate an average. If we have the same measurements, it will, and we perform a measurement 100 times, it doesn't make sense maybe to sum up that measurement, but rather to calculate an average instead of an individual, instead of a sum. So, and we can put it instead of the individual transactions or the measurement for the quantitative attributes. For qualitative attributes, we can either skip or count them and then replace the qualitative attributes with the values of a count. So maybe we can count how many data elements are of a category small in our data set. Maybe if we are characterizing some quality of some manufacturing, we can have a defect levels, we can have a quality somehow categorization, and this can therefore, instead of having individual fabricates of a certain product, we can actually just have the count of products which have been characterized with a good quality. And that can replace the individual occurrence of the objects. So we can reduce the memory, but also show the data under different scope and stabilizes the data to see the trends and does not give prominence to some random noise. For example, here we can see how such an aggregation can change the view on certain aspects related to weather. We have a precipitation at a certain area, so this means how much rainfall is coming to that spatial area, and we have a monthly characterization and a yearly of standard deviation. This means that we are interested to know how much does the weather change, how much does the rainfall change, and we can, with a high number, the rainfall changes a lot, while the low number of standard deviation means that the weather doesn't change that much. And we can see here that there are standard deviation for monthly and yearly precipitation differs. So if we aggregate for monthly precipitation, we can see that the standard deviation has a peak between 2 and 4, and it has practically no values which are smaller than 1 as a standard deviation. While if we perform the aggregation on a yearly basis, we can see that the standard deviation suddenly is very getting, there are elements which are getting close to standard deviation 0, but then the peak is, as we call it, mode in the future, will be around 1. So the standard deviation of when the aggregation is yearly over precipitation will become 1 for the particular area or a number of land locations where the weather was deviating. This is aggregation is one way how we can handle the large data. Another way how we can deal with large data is through sampling. So sampling is a way how we can take the entire set of data objects and we can create a subset of the data objects which is smaller, which is analyzed instead of the entire data set because the entire data set is too big. We need to be careful with this sampling process because sampling process needs to represent the original data well. So the samples need to be representative. If it has need to have approximately together in the new data set the same property as the original data set, and their mean should be close to the original data. Imagine that we have a data set which just measures point samples of a geometry on a geometry of a car. So we have a car and we are measuring spatial positions on the surface of that car. Now imagine that we have a lot of samples. We have way too many to be able to handle with our algorithm. However, we need to somehow take a set of samples which will be a good representative ones. So what does it mean, a representative samples? Maybe if we consider an overall length of a car or width of a car or height, which can be obtained from the seeing the dense samples, if we perform the sampling or subsampling, so we take representative samples, these characterizations of width, height, and length should be preserved in that new sampling set. There could be other characterizations which could be affecting or controlling our sampling process, and in order to achieve the desired set of samples which would be representative. What could be a typical sampling strategies? Well, one sampling strategy could be simply to perform random sampling, where we take a random sample from our entire set of data objects. Another could be sampling, random sampling, but without replacement, meaning that once we take that sample and we continue sampling, we will never again take that sample and consider it. Another will be sampling with replacement, meaning that the same sample object can be twice or more times in the new dataset. Or we can have something called stratified sampling, where we, let's say in the case of spatial domain, we discretize that domain into number of cells, so that which cover the entire area of space we want to have samples from, and we will ensure that at least there is a certain number of samples coming or covering each of the cells. So let's say there need to be 10 samples per certain area in order to have a good subsampling strategy. This would be called the stratified sampling. We can see that the sample size is affecting the performance. If we have too many samples, that defeats the purpose of sampling because the algorithm will not be able to perform. If we have too few, we can miss or create erroneous patterns in the data. We can see it here. Not sure what this object is, but we are sampling it, and we can see that some samples are more densely representing the structure, and in some areas there are very few samples, as if there would be some kind of void space which cannot be sampled. Maybe this is an engine and or something like that, some fabricate, and these are simply the areas where there was no possible to perform sampling because there was maybe the metallic part was this thick, and we are simply just measuring the parts outside that metallic component or something like that. Well, if we reduce the number of samples and our number of samples is suddenly very few, we will be losing that structure, and that might be undesired. that might kind of defeat the purpose of the analysis, because we will lose the information of where the void spaces are. Like, for example, maybe the ideal subsampling representation could be here, where both the number of samples is tractable by the algorithm, but the essential structures are still well preserved in the subset of the samples. So in case of we have well-separated clusters in our samples, we can, for example, perform sampling, and then we can measure the intersample distance, and with that we can understand whether we have represented all clusters in our data or some clusters might be missing, and that could guide the sampling process. That would be called something like progressive sampling, where we gradually increase the sampling count based on some and measure the accuracy profile. So until we sample until a certain desired accuracy is achieved, and then we can stop. Another data pre-processing technique is called, or family of techniques, is called dimensionality reduction. That means that in case we have a huge amount of attributes, we can reduce this number of attributes to a lower number. And this can be done in several ways. For example, if we have a certain hierarchical scheme, then we can use that in the dimensionality reduction. Imagine that we have various categories in our, let's say, basket analysis data. For example, that we have products which are related to certain breads, various kinds of breads, maybe a dark bread, a white bread, various forms, various corn used for the bread creation, and each of them is in one separate attribute in our data matrix, and this attribute is asymmetric. We could maybe just collapse it into just one attribute, being the bread, and that can be used for the analysis. Or diaries can be put into as one attribute instead of various more detailed representation of diary products. So that could be one strategy how we can reduce the dimensionality. However, we can reduce the dimensionality in other ways as well. So, for example, the document matrix is containing thousands of words or time series with thousands of dates, and we can reduce the number of words. For example, similar words or with similar meaning can be replaced by in this way, or with the time series, we can, for example, reduce the time resolution, and by that reduce the dimensionality. So this can lead to less noise and maybe elimination of irrelevant features. That could lead, because this data is then used for creating of certain kind of models of that phenomenon. Those models can be better understandable because they will have less attributes. And they could be more easy to process, but also more easy to read by humans. Data can be then more easily visualized because if we have, let's say, just two attributes, we can just easily plot it on the two-dimensional in the two-dimensional representation. Algorithms dealing with less dimensions can become more efficient, and so we can, for example, perform this dimensionality reduction by the method of feature selection, which uses subset of attributes. It's like a sampling, but the sampling was on the choosing rows of our data matrix, while feature selection will be choosing columns in our data matrix. And we will just select those features which are the most important for our data mining approach, which is studying or should answer some particular questions. So with this, we are not somehow aggregating the data, as I mentioned the examples before, but instead we are just choosing which attributes to we select and which not. Entirely different approach will be the so-called principal component analysis, which creates new attributes by a linear combination of the original attributes into a single new one. And this principal component will give us information in which combination of attributes makes the biggest change in our data. So it's characterizing our data in the most representative way. We can also, for example, perform feature weighting, which uses some importance measure to define important features, and that could then guide our process of feature selection and select if we have just a budget of 10 features, we can choose the features which have the highest importance in our among the set of attributes which the entire data set is having. With increasing dimensionality, we have the complexity that our algorithms need to deal with more dimensions, and this is already quite challenging. But the term curse of dimensionality refers to a phenomenon that many types of data analysis becomes much harder as the dimensionality increases, and not really like linearly harder, but really exponentially harder. And with one of the key problems is that with each new dimension, the data becomes increasingly more sparse. Like imagine if we have just this single dimension and we have some intervals, like 1, 2, 3, 4 intervals here, and let's say we have samples, and in each interval we have just 4, or no, let's say we have just 2 samples, then we have 1, 2, 3, 4, 5, 6, 7, 8 samples. Now, if we will have, this will somehow characterize our data along one axis very well. But if we have just 8 samples and we represent them in this two-dimensional we increase the dimension to 2 dimensions, suddenly we will have guaranteedly a situation where in one cell there will be not a single one sample, because we have only 8 samples in total. So the space of our domain will become much sparser. Here we have a relatively dense representation where in each of these intervals we have 2 samples. Here we will have on average less than 1 sample per one cell. And then if we increase that even further to a 3-dimensional case, with our 8 samples, we will not be really able to represent many cells. So we will need much more samples in order to characterize the 3-dimensional aspect of our phenomenon, or our phenomenon according to 3 different aspects with many more samples than if we just study one aspect instead. So here, as you might know, we have 27 cells for 3x3 case. So here we had like, this was, if this is 3 only, we will have only 6 samples. So 6 samples will be much less than 1 sample per cell in the 2 dimensions. And for the 27 cells, this will be a very few samples, very few cells will receive 1 sample, and with very high likelihood no cell will obtain 2 samples. So this is the curse of dimensionality, that if we are increasing the dimensions, the data becomes increasingly more sparse. And that has a problem, because classification, meaning assigning some class to a to an object by estimation, like maybe if an object belongs to one category or another category. This means that typically this classification can benefit from certain clustering, that one class is somehow represented in the whole data space as a certain kind of a denser core, and it is far from other categories. But if we increase the dimensions, then the distances between different objects will become not as clear as they were before. Without the dimension, the distances will become larger in that space, and the understanding of intercluster and intra-cluster distances will become much less distinctive. So this dimensionality might also, growing in dimensions, might also create us problems with being able to recognize certain clusters, because the distances between the data objects will be more or less the same, whether they are forming the same cluster or not, with these increasing dimensions. Therefore, reducing the dimensionality is a very important step in data processing in many pipelines, and it can be approached by for example, the feature selection, but also by the principal component analysis, which is coming from mathematical methods of linear algebra, and this method is basically just like instead of having maybe 5, 10, 20, 100 or 1,000 dimensions, 1,000 attributes, we will just pick or create 2 attributes, which are the linear combination of the previous attributes, and they will be somehow characterizing our data from the perspective of 2 axes, new axes in the data space, along which the data can be best characterized. So we can imagine that a data is somehow in many dimensions forming some kind of an ellipsoidal shape. So the samples are like forming some kind of ellipsoid in this multidimensional space, and the principal component analysis will be able to find out that there is an ellipsoidal shape in these multiple dimensions, and will be able to extract the 2 principal axes of the ellipsoid as the main axis which characterize the data spread in the 2 most representative directions. How this can be done? Well, this can be approached in the principal component analysis, can be approached by the methods from linear algebra, which is called singular value decomposition, which basically operates on the so-called data matrix. The data matrix, which we have already discussed before, is a set of data objects in rows and the attributes in columns, and it forms us some kind of matrix X with n rows and m dimensions, or m attributes. So, and with the singular value decomposition, what we will be doing is to decompose this data matrix into 3 matrices: matrix U, matrix S, and matrix V transpose, which multiplications of these 3 matrices will result in our data matrix. And the singular value decomposition will basically be able to find us these 3 matrices. This is very relevant for the principal component analysis, because basically the matrix V will have in its columns the principal component axis. So the vectors which will be in this column will be basically giving us the directions of the new axis within that space. Imagine that we have like a 3-dimensional space of three attributes, and this principal axis will be just one axis which will be going through this three-dimensional space along the spread of the data. So we can characterize that which one is the principal component directions within the vectors which are forming this matrix V, but in the way that we look at the singular value S, so which is also the decomposition of this data matrix, and this matrix S has only diagonal entries, and one of these diagonal entries will be the highest value, and that will characterize as the column in which we should look for the principal axis PC1. And then the second highest singular value in the matrix S will be defined as the column of the matrix V, which corresponds to the PC principal, the second principal axis, the axis which is explaining our data set in the second most representative way after the PC1, and is orthogonal to the principal direction 1. Let me explain you a little bit when diving into linear algebra, how can we calculate the principal components based on the calculation of singular value decomposition. In order to be able to perform singular value decomposition, in the simplest way would be to bind this calculation to our already existing knowledge from linear algebra on how to calculate eigenvalues and eigenvectors from a matrix. So if we have a matrix which is matrix X, and it is a symmetric matrix, and it is positive definite matrix, then we know that this matrix will have real valued eigenvalues, and it could be decomposed into two matrices, basically matrix Q and matrix T, and then also inverse of matrix Q, which will be actually the transpose of the matrix Q, and then these three matrices multiplied together will form as our matrix X. So in our case here, in the case of data sets, our matrix X will be in fact a matrix, data matrix, and it will not have these properties which I just mentioned. It will not be a square matrix, it will not be a symmetric matrix, and it will not be a positive definite matrix either. So this will not be directly applicable to perform the eigenvalue decomposition, but we will see how it is applicable in the indirect way. So we want to decompose the X into these three matrices, and that can be done by finding out what are the eigenvalues, and then from this lambda, which are depicted here as lambda, and what are the eigenvectors with which the following equation is satisfied, that the multiplication with the vector with this matrix, and this vector is non-zero, will lead to a zero. So in order to find this out, so we have, this is one of the fundamental equations of linear algebra, we are finding the matrix, for the matrix X, the corresponding eigenvalues first, and that can be done in such a way to fulfill this relationship. We can rewrite that relationship by sneaking in an identity matrix here, which will not change anything. It will just distribute the lambda values along its diagonal instead of the ones. And then as they are equal, if we subtract one from each other, they should be equal to 0. And then that will mean that if we take out the X, which is a non-zero vector here, this will therefore need to be 0, and that means that this matrix will be a singular matrix, because and the singular matrix means that its determinant is actually 0. So for generally calculating determinants is not that easy, but for our example of 2 by 2 matrix, it is relatively easy because we can multiply this term, which is now this matrix here. So it's x minus lambda I, which will mean that we will have on the diagonal, we will subtract lambda from the original values of our matrix X. So we will have x11 minus lambda will be multiplied with the term x22 minus lambda, and it will be subtracted by the product of x12 and times x21. And we can see that here, where this is already now multiplied out, and we can see here that this becomes, because these all terms are known from the matrix, so we just have a regular quadratic equation to solve, and we are finding the roots of lambda 1 and lambda 2 of this quadratic equation. So there could be either no solution, there could be a solution where the no solution means that in the real domain, so the lambdas will have be complex numbers, or that we have just one solution where the discriminant is will be 0 in the calculation of quadratic equation, or we have an result where we have two solutions which are real numbers. So in case of the matrix, positive definite matrix, we will have two solutions, and then these two solutions of lambda we can put, and they will be forming as the matrix T. This will be the diagonal matrix defined by the entries of lambda. Now, to find the corresponding eigenvectors of the eigenvalues lambda, we can just use this equation and find out for which, given a certain lambda, what needs to be the value of x so that the result will be equal to 0. And as there are in principle, infinitely many solutions, because we can just scale x arbitrarily, and every scaled version of one solution will be also automatically a solution. We will therefore just set the value of one of the coordinate of x, let's say x2, to a value 1, and then we will just calculate the x1 for a particular lambda 1. And from that, we will obtain the non-normalized eigenvector. And in order to have the normalized eigenvector to form our matrix entries, which will be a normalized containing normalized vectors which are orthogonal to each other, which is called so the orthonormal set of basis vectors will be forming as this orthogonal matrix. So we need to normalize that first eigenvector, which is associated with the first eigenvalue. And then we will need to also perform it for the second time for the second eigenvector, and then we will calculate that eigenvector in the same way, and based on the second eigenvalue, and then we will be able to find out this matrix, which will be what in graphics we call a rotational matrix, which is an orthogonal matrix, which is forming this decomposition into the two matrices Q and D, where the D is the set of the diagonal matrix containing the eigenvalues, and the matrix Q is containing the eigen vectors as columns, and the Q transpose is containing the same eigenvectors as rows. So how does this relate to our problem of principal component analysis? Well, a principal component analysis is based on, or can be based on, calculating the singular value decomposition, and singular value decomposition can be actually calculated in this eigenvalue calculation, and I will show you now how. So let's have a look at the singular value decomposition. Unlike in the previous case, we can perform singular value decomposition on pretty much any matrix. It doesn't need to be positive definite matrix. It doesn't need to be a square matrix. It doesn't need to be a symmetric matrix. It can be just any matrix. And this matrix X can be decomposed into these three matrices where this is the singular value matrix, which is again a diagonal matrix, and this is an orthogonal matrix, and this is also an orthogonal matrix. They just have different dimensions if the number of rows and number of columns of X is different. Why is this relevant for the principal component analysis? Is, as I mentioned, the matrix V is containing the columns of our principal components. According to the rows of the singular matrix, those singular value, which will be the highest, will be defining as the principal component 1 column in the matrix V, or row in the matrix V transpose. We have to be careful about that. So that's all good, but if we have this singular value decomposition, how does that relate to our decomposition of the eigenvalues? Well, it relates in the following way. Imagine that we construct a matrix N, which is simply just X transpose times X, and this will generate, actually, if we assume that X can be represented by the matrix product of U, S, and V transpose, then this matrix X can be, or transpose can be replaced by this values or the decomposition, and this decomposition. So this is the product of these two matrices, where once the X is transposed, and that will lead to if we have transpose and transpose, this will lead to different order, and this one will be untransposed, and then the S will be transposed, and the U will be transposed. So V will be untransposed first, and S will be transposed. But it is not transposed written here, because transposing a diagonal matrix is the matrix itself, and then we will have U transpose, and then from this other matrix decomposition we will have the U, S, and V transpose, and we can see that these together, as they are orthogonal matrices, they will be forming us together an identity matrix. Therefore, we can actually take it out, and we will just have a product of these three matrices, V, S squared, and V transpose, which is exactly the same form as we have for our eigenvalues. So if we have our eigenvalues, we just out of our matrix X will need to calculate our matrix, the diagonal matrix, sorry, the square matrix X transpose X, which will be then used for the eigenvalue calculation. The eigenvalues will be 2.618, and the second eigenvalue will be 0.382. And then out of this, we can calculate the S matrix, the singular matrix. But so you can see that the lambda 2 and lambda 1 are not represented here, because we have calculated these lambdas will be forming as the S square matrix. So this is not the matrix which we are eventually interested in, and therefore we need to perform a square root of these values, which is actually the entries along the diagonal. Based on these values, we have, or actually these values, we can calculate our calculation of our V, and the V will be calculated in this following way, again as eigenvectors of this decomposition, in the same way as I described it in the previous slide, and we will find out that one eigenvector of V is 0.5257 and 0.8506, and the second eigenvector is which is orthogonal to it, is having these coordinates. So with that, we have actually performed the principal component analysis, and the PC1 is this axis, and the PC2 is this axis. So this tells us that in principle, for these two data points, if you like, if you look at it from the perspective of a data matrix, then and it's two attributes, we are the second attribute is much kind of more representative, and the first attribute is is not as representative. So we will have our data principal axis will be kind of a little bit like going into the direction of the second more along the second axis, more along the second attribute. So, and the second principal axis will be just orthogonal to it. So with this, we have described the process of principal component analysis on a very simple example. In the case of a real data matrix, we will have maybe thousands of rows and maybe 5 to 10 columns, and actually our matrix V will be the matrix of the attributes, so it will actually be a 5 times 5 matrix, and the U matrix from this singular value decomposition will be actually a 1,000 times 1,000 matrix. So this is more a data, the U is more the data object matrix, while the V is the data attribute matrix. And from there, from the matrix V, we will be obtaining the principal components. Now that we have finished calculating the principal component, we can think about whether this sort of makes sense. So we can see that the principal component is pointing somehow upwards, and we can think of that this is like points upwards. But if we look at our data, it's like has an x component is 0 and y component is 1, so it lies like at the y equals 1, where the y-axis is crossing the x-axis, but at the elevation 1, and then the other point is at 0.11. So these two data points are sort of forming a line, and this is a horizontal line. So y is equal to 0. Therefore, this vector should be rather like 1, 0, and not really 0 0.5, 0 0.85. So something is wrong here. So somewhere although we did the principal component analysis almost by the book, there must have been something wrong. So where did we make a mistake? So there is one thing which we forgot to do, and that is that the PCA works on the mean-centered data with normalized dimensions, meaning that we first need to center our data around the mean, and then if we have our data dimensions on different scale, we need to normalize them by their standard deviations. So we didn't do it. And that was the problem. So we need to center the data matrix first, and we will create somehow the centered data matrix around the mean. So the mean of axis is what? Is 0.5. And therefore, if we are centering ourselves by 0.5, then we will move this we will move this interval into the interval minus 0.5 to 0.5. Then the center, the mean of these two lies at 0. So that's what we needed to do first. And the same for the y attributes. And there 1 and 1. What is the mean is 1. And if we center that around 0, then it must be 0. So this is actually our matrix X, which we need to work with, which we need to perform the singular value decomposition on. So we assume that the attributes are already on the same scale, so we will not do this normalization by the standard deviation in this case, but we did perform this centering. Okay, so now how can we continue with this to get the correct principal component? Well, again, we create this matrix, which is the product of the XC transpose and XC, which will be therefore a symmetric matrix. And here is how we calculate it. So we have here the transpose of the XC, here is the XC. And if we multiply that out, we end up with this very simple matrix, which is symmetric, but it's also diagonal. It has zeros almost everywhere. And therefore, we can right away read off what is here the eigenvalue of this eigenvalue decomposition of this matrix, and that is eigenvalue 1 is 0.5, the other one is 0. So for the eigenvalue 0.5, let's compute what will be the eigenvector when this is clearly the bigger one, so it will be corresponding then, even if this is not the singular value, because that will be the square root of this, but they are related clearly, and as this one will be clearly bigger than square root of 0. So we are now calculating with the bigger one what is the corresponding eigenvector, which will be the vector in column vector in our V matrix. So 0.5 minus lambda 1 and 0 minus lambda 1. So this is 0.5 minus 0.5 is 0, and 0 minus 0.5 is minus 0.5. So if we have this matrix multiplied with our V1 eigen vector, here are its x and y components. So then if we observe this second row where there is actually one at least component is non-zero, that will lead to the equation where 0 times v1x minus 0.5 v1y equals 0. And therefore, this will be cancelled out from the equation, and therefore this means that the v1y must be equal to 0, and that means that for this to be a vector, unit vector, then it will need to be some value 1 here, so that this is a unit vector. And with this, we will have constructed the eigenvector, which actually corresponds to the principal component. So 1, 0 is the vector which goes in the horizontal direction, and this is the correct principal direction which we should have calculated in our case, and we would if we wouldn't make the mistake of not centering the data matrix around the mean first. So going back to the discussion of data preprocessing and dimensionality reduction, we do not want to now engage any further into the linear algebra, but it was important to understand how to calculate the principal components in one way, maybe not the most efficient way, maybe not how it is usually calculated in the current data mining or knowledge discovery systems, but it is the easiest to comprehend from the perspective of being well versed in linear algebra operations and structures. So another approach how we can reduce dimensionality is by means of feature selection. So, and that could be, first we should remove certain attributes which are in a way redundant. They are not really duplicate, but they are redundant. Like for example, if we have a transactions matrix, then or records, we can remove the VAT, because VAT can be calculated as an attribute from the overall sum before the tax. And the total sum can be also removed, and maybe only the value before tax can be stored. Then we can also remove irrelevant features, like in case of the some kind of a student type of matrix related to university courses or some other aspects, the student ID is not really informative attribute and can be removed as well if we want to calculate some insights from this data. The ID information will not provide us this data, this insight. So, and then we can try, in principle, ideally, all subset combinations and choose the one with the best results that would lead to the best outcome of our data mining solution. So we can reduce it to just one attribute, two attributes, and have all the possible combinations, and the one outcome which gives us the best results. Given a certain task, we could choose as the desired feature selection process. But that would lead to exponentially many combinations, which would then, the data preprocessing stage will explode the computational costs and will not be permissible. So therefore, we can think of dimensionality reduction or feature selection as three different strategies. So, for example, embedded approaches are methods where the feature selection is an integral part of the data mining algorithm, like, for example, in decision trees. So there, the feature the feature selection is not part of the data preprocessing, but it's actually performed during the data mining algorithm itself. Another approach could be to, before we start with the data mining solution, we can filter the data set and just choose those attributes which are relevant for the data mining algorithm before it starts, and set maybe one approach could be to select set of attributes or dimensions where pairwise correlation is as low as possible. Because if the attributes correlate, like, for example, the VAT highly correlates with the actual total sum or the value of an item before the taxing, which has a perfect correlation. This basically, the correlation is giving us information about the redundancy of that attribute. So if we have as low correlation as possible in our attributes, that will mean that our feature selection is probably telling us the most about most different aspects about the data. And there could be wrapper approaches which use target data mining algorithm to find the best subset of attributes, but not by considering all possible subset, but also only considering some of the subset. So while in this approach, we are using it as we are using a different type of heuristic, if you like, to find the desired feature selection. Here, we are actually using the target data mining algorithm for the feature selection before the data mining algorithm really actually performs its let's say, desired calculation. We will run several runs of data mining before the one which will be finally resulting in a model or outcome we desire. So for the feature selection, we can think of a specific architecture for the filtering and wrapper approaches. Not so much for the embedding, because the embedding already contains the feature selection as the integral part of the data mining algorithm. Here, we still consider the filter and wrapper as external pre-processing parts of the features before the data mining algorithm is done as a feature selection techniques. So we can use actually during this feature selection a search over all possible subsets of features as we can use kind of a search structure. Like, for example, maybe a search tree could be an approach. Where the filter estimates the data mining algorithm performance, like we had this minimal correlation, while the wrapper actually uses the data mining algorithm for feature selection scoring. We will stop with the feature selection process when we find the subset which has the best performance and size, and the stop criterion can be the performance or the size of the subset, or actually number of iterations when we are searching for the selection of the features. Then, after we are done with the feature selection, the subset selection is validated through some tests against its performance of the original feature set. For example, we can use multiple feature selection algorithms and compare the results of the data mining algorithm of each result of those. And we can see that process here schematically represented, where we have certain attributes at the beginning, and then we perform certain search strategy. And then after the search strategy is completed, we have a certain set of attributes which are then the maybe most beneficial, and this is done based on some we evaluate this subset of attributes either by the filter or by the wrapper methods, and then we have a certain stop criterion whether this subset is good enough or it's not, and then if not, then we still again search again, and we are performing this loop until we are having the certain stop criterion, which means that we either ran out of iterations or we ran out of the size of the permissible, which is permissible for the subset, or we achieved some desired performance in this evaluation process, and then we are done. This could be, so we have selected attributes, and in this validation procedure, as said, we can have several feature selection algorithms, and then we validate in this step which one performed the best on the data mining algorithm, and then they choose the one which performs the best. So this is in principle the way how we are performing the feature selection, and it will give us the representation of our data set which is permissible for the data mining algorithm to process efficiently. Related to feature selection, we have a different approach and strategy which is called feature extraction. Feature extraction, unlike feature selection, doesn't use the same attributes, but is actually generating new attributes, new features from the original attributes, and creates a feature vector which is different from the original vector of features which the original dataset was formed by. So in this sense, the principal component analysis can be seen a little bit being the feature extraction method. But we can have also different strategies here in mind. Like, for example, we can imagine an example of attributes of which are characterizing a pixel in an image. So originally we have raw pixel values, but instead of these raw pixel values, we might perform an extraction of features which will be characterizing that pixel, and maybe be characterizing that pixel based on neighboring pixels. So here in feature extraction, our intention is not necessarily to reduce the amount of data, of dimensions or attributes, but actually sometimes we are increasing that amount. Like, for example, in the method which is called scale invariant feature transform, we will be generating a 128-dimensional feature vector, which will be representing just a pixel. So we will explode the representation of RGB which was characterizing by three attributes a pixel. We will have suddenly 128 attributes per pixel, and this information will include then information about neighboring pixels to measure the difference between them, or measure to find some edges or some color gradients. So in case of SIFT, the scale invariant feature transform, we will generate for each pixel this feature vector, which will be characterizing it, and it will be scale invariant and also shading invariant representation of a pixel, so that we can find the same spatial point in different images which have been taken from the same object, for example. But that goes a little bit outside the scope of this lecture. But the scale invariant feature transform will be a typical feature extraction method. And then feature vectors are, in the case when we talk about feature extraction, are often engineered based on a specific domain and domain application characterization. So if we want to, for example, perform image matching procedure, image registration, we will have the scale invariant feature transform engineered based on this goal and not for other goals in mind. We need to say that if we perform this feature vector extraction based on learning, based on machine learning, while we are training a model, we call this feature vector a latent representation. So a latent representation will not be a feature vector which has been engineered. A feature vector will be a representation which has been learned by the machine learning algorithm itself. So, and features can be therefore constructed from existing attributes by complex mathematical formula, such as calculating density as a ratio between mass and volume. So we can actually perform some physical calculations in order to construct new features. So from previous quantities, we can generate new quantities, and by that transforming the data set into a set of new features which are physically characterizing the data set in the same way as the previous features, but becoming more relevant for a given task. Similarly to feature extraction, we can also perform feature transformation where we will transform our problem to a new space where the problem or the data can be easier to analyze. One such an example is spectral analysis. That means that we will transfer our signal from the original time domain or spatial domain to a frequency domain, where in the frequency domain we can easily spot the signal and differentiate it from the frequencies which are attributed from the noise. You can see that example here. We are talking about the frequency transform here in particular, but there could be other approaches that are related to spectral analysis, like for example also wavelet transform. But there could be also simpler transforms, like for example moving the problem from Cartesian coordinates to polar coordinates, or representing the function as derivatives. These all somehow are representing the same type of family of strategy of dealing with the data. We can see here that we have a regular sine wave here, and perhaps this sine wave actually it's one which is with full line, and then there is another sine wave which is a dashed line, as you can see here, and these two are summed up together, and they are also interfering by that, because if one value is positive while the other one is negative, it can be easily then summed up to 0 or close to 0. So this is one aspect where we have a signal which consists of two different waves which are contributing to the signal, and on top of this signal we add an additive noise which will generate this temporal signal representation, where we can see that there is some kind of maybe oscillation, but not really, we cannot really see it, but at the same time there is a lot of noise which we can see very clearly. So the signal is definitely buried and behind the noise, and it is also convoluted by the fact that we are having interference of two signals which are somehow in some sense canceling each other. If we take this signal and we transform it to the with a Fourier transform into frequency domain, that means that we represent this signal by a series of cosine and sine functions of a different period or different frequency. Then we can see that certain sine waves and cosine waves are represented there very very strongly, like these two peaks, and then we have also some other contribution from various other frequencies of high frequencies here. And we can easily see that our two original functions, meaning the two sine waves of different period, are represented here. This is the one which is the cycle is let's say around I don't know 8 cycles per one unit. 1, 2, 3, 4, 5, 6, 7, so something like that. And then the other one is where it is maybe 15 or something like that. That is the dashed one. And we can see both of them are representing as strong peaks forming this frequency decomposition. And then there is a lot of signal which is formed from this noise representation. If we just cancel this noise representation and maybe just by thresholding everything what is less than 100 will be just put to 0 frequency and transfer it back, we will recover a beautiful representation of this signal. We can also even take one signal away and then represent just one, and then we will have just one sine wave, and then the other one, and then we will have the other sine wave. And with this we could completely reconstruct the signal just by transforming the problem to another domain. There are situations where the data preprocessing will require that our data is binarized, meaning that we represent our data by some kind of binary code, and we have to transform it, therefore, from its original representation to this binary one. This is very typical if we are dealing with categorical variables, like, for example, something which is between bad and good or great, and we simply have this categorical nominal qualitative representation. And then we suddenly, for a particular attribute, and then we suddenly need to perform classification. Often the classification or algorithms like a priori or FP growth would require us to find some binary representation for this. This is not that difficult to perform. Like, for example, we can imagine that we associate this scheme of, in some sense, ordered categorical values with an integer scheme like 0 to 4 for these 5 different variable values. And then we simply represent it with the binary code. So for digits from 0 to 4, we will need 3 bits, and then for 0, we will have 0, 0, 0, 0, 0, 1 will be the encoding for 1, for 2, 0, 1, 0, and 3, 0, 1, 1, and for 4, we will have 1, 0, 0. And this might be sufficient for some algorithms. However, for some other algorithms, like, for example, encoding of multiple classes, we typically would do it by the so-called one-hot encoding. This means that we will have a vector of the same number of bits as we have of our classes, and only then the classes will be represented by 1 if it is representing the particular value, and the rest will be 0. So the one-hot encoding means that, for example, for the awful, we will have the x1 will be, which is a binary variable, will be represented by 1, and the x2, x3, x4, and x5, which all form the value of the awful, will be set to 0. So this is called one-hot encoding, because the 1 here will be representing just the one state in a way, while there is, like, with highest probability it's awful, and with 0 probability is poor, with 0 probability is okay, with 0 probability is good, and with 0 probability is great. So this is how this will be typically used in classification tasks. So And then with such a one-hot encoding, we will have for the other one, it will be 0, 1, 0, 0, 0. And then for OK, it will be 0, 0, 1, 0, 0. For good, it will be 0, 0, 0, 1, 0. And for great, it will be 0, 0, 0, 0, 1. So this is a way how we can represent categorical variables if we want to perform the classification task, especially when we are using some probability and statistics approaches like typical for machine learning based classification. So in the case of the binarization, if we are just using the binary code, we can take m number of categories, assign each category a unique natural number, and then use the binary code for the binary representation. With that, we will be using only log2 of m binary digits for representing all the category values. If we have the problem with one-hot encoding, we will need to have m of these digits, binary digits, to represent as the values. And one needs to say, in case of one-hot encoding and some kind of classification tasks, these will actually become real values like probabilities and will no longer be binary if we should use some probabilistic methodologies. Discretization, on the other hand, is a process where we are turning a continuous attribute into a discrete one, like you could say an integer one or maybe an ordinal one, perhaps. So in this case of discretization, we would have values which will have any real number as a possible value, and we will be turning this into some kind of discrete values. The typical strategy would be to form on the continuous axis some kind of bins, and in these bins the individual data element will be falling. So here you can see some kind of original data which is on the x-axis distributed around 7.5, 10 and 15, and then there are two outliers at 0 and 20, and here we can see that the ideal separation will be maybe perhaps like between here, maybe then here and here, but also possible would be the one which is somewhat clustering these two because they are very close together. So, but now imagine that we are performing a discretization, and the discretization, which is kind of not really looking at the distribution of the values, will be maybe to discretize it into equal width intervals. And if we have this interval by 5 here, we can, and a reasonable idea could be think of, let's discretize it in such a way that we have like one bin which is for all the values which are smaller than 5, then between 5 and 10, and then between 10 and 15, and then 15 and 20. So this sounds like a reasonable uniform split, but for this type of data particularly, which is concentrated around it is having several peaks or modes, if you like. So unimodal, bimodal, trimodal, quadromodal distribution here. And in this distribution, it would be good if this one mode can be sort of in one bin and not separated. However, our uniform discretization has, with the equal width, has actually discretized it just exactly through the mode, which was unfortunate. It's a coincidence, might be much better in other time, but we never know if we don't employ some kind of data guided scheme for the partitioning. So another approach which can be used is the discretization is the equal frequency, which means that we will have the same amount of elements in each bin. And here the situation is getting a little bit better, perhaps, in the sense that we have one bin which is representing as the mode around 5 plus this outlier, but still a lot of these elements which somewhat correspond to the the one mode around 5 are already separated into another bin together with the values around 7.5, which seems to be here. 10 seems to be relatively nicely separated, and the 15 is separated partially well, but still there are several elements which would fall into the bin, which is kind of more associated with the value 10. So the equal frequency is another type of binning scheme or discretization scheme, and might lead to more or less satisfactory results. So therefore, it would be good to have some kind of still maybe unsupervised discretization method, but this discretization method will give us will be taking into account the number, the bins where would be good to separate them. And an excellent technique for that is k-means clustering, which is a parametric method where we need to define the number of clusters. And once we specify the number of clusters, then it will give us a reasonable clustering in such a way that it will establish k-means, values which will be a means of separate clusters, and then it will be setting the borders in such a way that these cluster separability, the inter cluster distances are the highest, while the within cluster distances will be the smallest. And with that type of categorization, we can establish here the k-means clustering, where we can see that it has been really fortunately finding if we set it to 1, 2, 3, 4 means, so 4 means clustering, will result into this very nicely well-defined separation into these 4 discrete bins. So that would be the technique which we will be also looking at some later point in time in this data mining lectures from the data analytics course. Then we have as discretization, which is supervised. And the supervised discretization could use some additional information, like, for example, the class labels, to maximize the purity of a given interval, of a given partition. So, for example, if we have the information about some data elements, which class do they correspond to, then we can set the boundaries so that the within cluster values, the values will be minimized, the distances, while the intercluster positions, intercluster distances will be maximized. Now, the approach to do that could be, for example, based by interval entropy. So with interval entropy, we mean that we will have used the entropy measure, which has been defined in thermodynamics and then sort of redefined in information theory, which is related to statistics and forms a separate theory on its own for signal analysis. We can use this entropy quantity as a simple measure of kind of uniformity. So entropy becomes very low if all elements are of the same kind and likes to, in some sense, have a different, maximize the variety or diversity in a set. So if the set is very diverse, the entropy will be very high because it basically measures the degree of unorder, if you like. So if it will be very ordered, the entropy will be very low. So in that sense, we can have a simple and effective way of defining, let's say, k classes with because of the k clusters which we have. So we have k classes, and we would like to form these k clusters, which mi values in each ith interval, where the mij is the number of values of in the interval I of class J. So now imagine that we have a certain separation into intervals, and we can characterize an entropy of an interval. So we go through all the elements which are in this interval I. So this is an interval or partition I, and here we will be looking at all of the different classes, and we will be formulating the sum of the probability of that class in this ith partition of the class J in the ith partition and its logarithm. So this is forming us the entropy value. And here we can see that the Pij is basically defining as the probability is measured by the occurrence of the jth class in the ith bin, and defined the number of those, and defined by the total number. So if this is 0, then this will be 0, the probability will be 0, and then 0 times this, so that this product is also considered to give us a value 0. Now, if we want to then find out what is the overall entropy across all the bins, we will simply perform the average of those bins. Like we multiply the amount of the entropy is always weighted by the fraction of how big is that bin by the corresponding elements in the bin, divided by the overall number of elements. So this defines us how big the bin is, and this is multiplied by its entropy, and therefore we will have some kind of average a notion of entropy defined, and we want to minimize this overall notion of entropy. If the interval has objects of one class, then the entropy will be 0, because it will have just like the probability will be either 0 or the probability will be 1, which will be leading in both cases to the entropy equal to 0. Note that in this particular case, to make it consistent with the book, we are not adding here the negative value, but normally the outcome will be a negative value of this, because we will have here the logarithm of a value which is like a probability, which will be between 0 and 1, and that will lead to some negative value. So then this, and at 0, this will be basically minus infinity, and therefore we need to have this agreement, as we do typically in entropy, that 0 times the log of 0 is equal to 0, which in limit holds, while this value here will be, if it will be, let's say 0.1, then this logarithm will be negative, this will be positive, so it will lead to a negative number. And we need to be aware of this inconvenience or simply mathematical consequence, and therefore this entropy sum will be a negative quantity. So if we want to, usually if we are dealing with entropy, we will have a negative sign here. So let's have a look at how this entropy-based supervised discretization plays out. We can bisect an interval first, so that the sum of the entropy of both new and of both intervals after splitting is minimized. So for example, here we can see that if we are splitting it into, let's say, I interpret this drawing as that we can split it either in 3 intervals along the x-axis or 3 intervals along the y-axis. So if we will choose the partitioning so that we have different partitions along the x-axis, we will be identifying that we have we can place a X partition. So we seem to have here like one class, second class, third class, and fourth class. And if we have these fourth classes and we place these three partitions, then two partitioning lines, in fact, then we will have here like one partition will be separating these values from the rest, and then this partitioning will be separating these values from the rest, and this will be in the same type of bin. And if we will be performing this partitioning somehow in the horizontal direction, then we can see that here is another one partitioning line, which is making the entropy low in sum for this region and for this region. And then if we have one more partitioning, then we will have the partitioning which will be separating then this region from this region here. So this could be the way how the partitioning is performed. There is also an alternative approach how this can be done. Maybe that is what this illustration is encoding here. And so what I would probably see as a reasonable algorithm here would be that first we will, in order to partition this, we will calculate along one axis, X or Y, the partitioning, which is partitioning this whole set of values into the smallest entropy. And that will, for example, be that we will take, let's say, the lowest partitioning scheme will be along the y-axis, where we will have here one partition, and here it will be another partition. This will be probably leading to the lowest overall entropy. And then we will then have this part, this half space, and this half space. And in order to get this half space to be separated into one cluster here and one cluster here, we will use then no longer the separation along the y-axis, but separation which is parallel to the y-axis, so along x-axis, x is equal to 4, and here we will be partitioning the one class from the other class. But it will only, this line will be relevant for the second half space, for y equals 2 or higher. And then we will have another partitioning line along the x equals 1 axis or line, where we will be partitioning this cluster away from this cluster. So this will be like a partitioning which is first like with the horizontal line, and then with one vertical line for one already half space, and then with another horizontal line for this other half space. And that will make a meaningful entropy-based supervised partitioning approach, which is then splitting with changing axis potentially into intervals with of the lowest possible entropy until the maximum number of intervals is reached, or the maximal permissible entropy is achieved, and then it's stopped. So we will stop after these three steps, because then we will find out that that for each of these clusters, if these are pure clusters, for each of these clusters we will have simply a value of entropy 0. Now, this is the entropy-based discretization is one of the supervised approaches, and together with the unsupervised methods can separate us the clusters quite reasonably well, or the values into clusters. Now, there could be also some other variable transformations, mathematical transformations, which will be able to separate us somehow the otherwise intertwined values from each other, such that the structures are suddenly or the points, data points, are suddenly becoming easily separable. For example, separable just by a line. And these type of transformations, which we could be frequently using, is, for example, absolute value, logarithm, x powered by some exponent k, or x powered by x, a reciprocal of x, square root of x, or sine x. All these are transformations which transform our original attribute values into some kind of features which might be more beneficial for the particular encoding and data mining algorithm. For example, if we have multi-scale problems where the data points are residing on several scales simultaneously between, let's say, millimeters up to kilometers, then we have a scale range of order of magnitude 6. So because we have 10 powered by minus 3 for millimeters of meters and 10 powered by 3 for the kilometer. And if we have such a case, maybe this is a way too big range to allocate somehow the data points, and therefore we can transform it perhaps by the logarithm, and we will then suddenly have only not 1 million different values between millimeter and kilometer, but in fact we will have just 6 values after the log transform. We need to be careful when we perform some kind of transformations which might be beneficial for separability of the objects, or generally for data mining algorithm to be efficient, that some transformations might, for example, give a different order of values. So what was previously maybe ordered from highest to lowest values might be after the transform ordered from the lowest to the highest values, or even for some highly non-monotonic transformation like a sine wave, it can be different. It can be bigger values, smaller values, and suddenly we will have the order completely mixed up. So we need to be aware of that, and we also need to be aware of that some transformations are applying to only a subdomain, like for example they are only valid for the x is bigger than 0, and there the transformation is happening, and for all the points where the for the negative values of x, either the transformation is undefined or the transformation is simply not transforming those points. A typical example will be, for example, the ReLU activation, which is typically used in machine learning, where it doesn't really do anything for the points which are having negative values, and which are having positive values, and for the negative values, it simply assigns to all of them value 0. Finally, we have something called standardization or normalization, which is typically a process which somehow brings our data variables or data attributes under the same type of distribution. So imagine that we have normally distributed values for a given attribute. However, they all have a slightly different mean, and they have all different standard deviation. And if we have such attributes with different means and different standard deviations, then we might experience that some variables which have maybe very large standard deviation might be somehow affecting how this which of the attributes will sort of dominate in the data mining process. So often we would like to perform some kind of normalization of the distribution, and to bring it, for example, to the standard deviation which is 1, and to a mean which is 0. So we can, for any normal distribution, we can transform the distribution to follow this normal distribution of 0 mean and standard deviation of 1. And we can do it in the following way. So first of all, we will find the mean, which is equal to some average value of all x's, and then this, which is this value here, and then we will perform the and also here is the value for standard deviation, and we perform this transform where the x prime is equal to x minus the mean value divided by the standard deviation of the distribution. And then if we perform this transform to all data points of this attribute, we will create a new variable which is following the standard normal distribution. And then this will be beneficial, because if otherwise the two variables will have different ranges, such as income and age. The age, many people will agree that the age is, let's say, something between 0 to 150, while the income can be something between 0 and 100 billion for some people. So then the difference, the range of the income is much higher than the age, and then in our analysis, this income will be dominating the analysis process. And if we do not want to have this unfair bias in the analysis with respect to the income, we can normalize the income with this process and also age, and then they will be both normally distributed with the same parameters. So if the range differences are ignored, the comparison will be otherwise dominated by the differences in income. So for a robust handling of outliers, if we do not want to have the outliers sort of dominating this process, we might also instead replace the mean with the median. So here we will take the median instead, and the median will then and the standard deviation could be also replaced with the absolute standard deviation, which formula is here, and then we will have a outlier robust normalization or standardization approach. In the next, we will be discussing the various measures of similarity and dissimilarity for various types of data. So similarity between two objects can be understood as a numerical measure of a degree to which these two objects are alike or dissimilar or identical. So, and we can measure it in some logical assignment would be that if they are dissimilar, then they are value of 0, and if they are similar, they are value of 1. However, this kind of similarity measure is not always matching what we can get from various types of measures. For example, a correlation measure, which correlates or measures correlation between two types of data variables. It could be both the spread of the attributes, but also two different objects, data objects, can give us a correlation value between -1 and 1, where the -1 is strongly negatively correlated. So there is a strong relationship between these two variables. They depend on each other very strongly, but in a negative way. So one is increasing, the other one is decreasing, and then one is a strong positive correlation. You can imagine, for example, for the strong negative correlation, like if we have a volume versus pressure. If we have increasing volume, we will be decreasing the pressure, and if we have the decreasing volume, we will be increasing the pressure. So there will be a strong negative correlation between a volume and pressure, while in the case of the positive correlation, we can have two variables which are strongly positively correlated, like, for example, the price and the VAT of the which is corresponding to that price will be having a strong or high correlation. So this is not the ideal then mapping because it's not between 0 and 1, and it is also questionable whether something which has a strong negative correlation, so it has a very high relationship with the actual value but in the negative sense, whether it is should be considered similar or dissimilar, because it is very tightly related. If we have, for example, correlation 0, we know that the particular aspect is not, two aspects are not related. That would be kind of dissimilar. But what does it do for the negative correlation can be a question of interpretation and probably depending on particular application scenario. We can, for example, decide that the correlation would be matched to the similarity in the way that we will take an absolute value from the correlation. That could be one option, but not always that will be a good fit. Then, for example, we can think of how can we define similarity or dissimilarity of an ordinal attribute. Like if we have on the scale poor, fair, okay, good, excellent, then what is the distance of similarity between these? So if we have poor and poor, then the value will be 1. But if we have poor and fair, what should be the value? The kind of the understanding would be that poor and excellent are the most distant from each other in this ordered ordinal attribute, and therefore maybe the one would be the distance between these two attributes should be the similarity should be equal to 0 because it has the highest distance. So if this is 0, maybe then we can decide that we will have like a equal distances between these two categorical ordinal attributes. So, for example, the poor will be versus poor will be similarity 1, to the fair will be, let's say, 0.75, to okay, the similarity will be 0.5, to good, it will be 0.25, and to excellent, it will be 0. So that could be this uniform kind of distribution can be used for defining the similarity among ordinal attributes. It can be easily calculated in some way that we give all these values some kind of integer value between 1 to 2, 3, 4, 5, for example, and then we will calculate like poor will be 1, 1, and excellent will be 5, for example, and then if we are performing the similarity, we maybe want to perform the calculation where the outcome of this calculation will be equal to 0. For that, we can, for example, find a reasonable formula expressed here. Like if we have poor will be 1 and good, excellent will be 5, so then 1 minus 5 will be minus 4, and then in absolute values this will be 4, divided by the number of categorical values, which will be in total is 1, 2, 3, 4, 5, minus 1 is 4, so 4 by the minus 4 will be giving us 1. For this similarity, it will be 1, and for similarity, it will be 1 minus dissimilarity, meaning that we will have similarity, it will be then equal to 0. So this could be a reasonable way how we can define it for the ordinal attribute category. Then for the interval or ratio, we can, for example, see that the dissimilarity can be simply an absolute difference, and then the similarity can be a different type of values, but for example, it could be one of these values. I believe here the book wanted to write 1 minus d again, so that we get the distance between, it's not negative value, but it is value between 0 and 1. So similarity between ordinal attribute we have defined, similarity between interval and ratio can be expressed by this kind of rather clear distance measure. So distance and dissimilarity are somehow mapped to the same, the same, except that the distance is distance 0 means 0 dissimilarity, so high similarity, but it is not bounded by 1, while the dissimilarity would be typically bounded by 1. Here, in the case of nominal values, we can only say whether things are similar or dissimilar, whether they are the same or not the same, and therefore the dissimilarity will be 0 if they are the same, and 1 if they are not the same, and the opposite will be true for the similarity. Now, if we are talking about the distances, it is important to define that there are many distance measures which we can take into consideration. For example, the most common will be the distance measure, which is the Euclidean distance. We have used an absolute of an Euclidean distance before, or or actually L1 distance before in this one-dimensional case. Here we have the distance for n-dimensional case, where we have not just we have two objects, let's say, and these two objects have an attributes each, and then we are calculating the distance between these two data objects. And here we can see how do we calculate it in the as a Euclidean distance. So we are summing up the square difference between the individual attribute values of the different objects. So for example, this is attribute I, maybe this is the age attribute, and age of one person minus age of a different person, and then we get some value out of this difference, we square it, and then we sum it up, and then finally we perform a square root operation, and that will give us the Euclidean distance, the air distance, if you like. If we are talking about positions in space on the map, then if we perform the different components in two-dimensional space, two components, and then we square them in x and y dimensions in that particular case. So here the objects are called x and y. In that case, the axes will be called x and y. So that will be a little bit of overloading. But anyways, then we will be performing the air distance measure with this Euclidean distance. Then a generalization of the Euclidean distance is the so-called Minkowski distance metric, which is calculated in the following way. So this is the distance, the Minkowski distance, which has a parameter r, which is the way how we sort of measure the distance. So if we have here the r is equal to 2, we will have the Euclidean distance. If it is equal to 1, we are talking about the city block or Manhattan distance. So, but here we will need to have this in absolute values in that case. And then we are calculating here various types of exponents can give us different values. So for 1, we have r equals 1. We are talking about the so-called L1 norm, or the absolute distance, or the Manhattan distance, which is a sum in two-dimensional case. It would be sum of x coordinate and the y coordinate on the map, while for the r is going to infinity, the supremum or the L max or L infinity norm is the maximum difference between any attribute of the object. So this type of distance will just take one, the attribute distance, it will just take one attribute and its distance for the attribute where there are the most distant values. So, and that will be then the highest difference when the r is going to infinity will be dominated in this sum, and therefore all the other differences will be neglected when we are then performing the square root, not square root, but when we are performing the reciprocal square operation. So For example, the Hamming distance is the L1 distance for binary codes. Imagine that we have binary data and we want to find the distance, then we will be performing just the distance will be, Hamming distance will be simply an Manhattan distance for the binary codes. If they are having the same, like 111 and 111, the distance will be 0. But if we have 0, 0, 0 and 1, 1, 1, the distance the Hamming distance will become 3 because each of these binary codes is different. So, and then we can also, for multi-dimensional case, we can also perform the so-called distance metric, which contains the pairwise distances between objects. So if we have so this could be between objects, or this could be forming us like where we are putting the objects in the both column and rows, and we will have then a distance between one object and the other object across all attributes, and the distance value will be in the content of the cell. And then with this way, we can quickly see which objects are close to each other, which objects are far from each other, and that could be the basis for example, a clustering algorithm. So, and we have some of these distance measures, so measures of dissimilarity, and in some sense, which will be then mapped to dissimilarity of 0 to 1, which could be mapped to similarity measures. These measures are typically could be, and that many of them, like for example the Euclidean distance, is called a metric because it fulfills 3 essential properties. And these 3 essential properties of this function, distance function, are that the distance function is always a positive value, so either 0 or positive, never negative, and then that the distance is only 0 in case when the x is equal to y and y is equal to, or the y is equal to x. And then also that they are symmetric. The distance from x to y is the same as distance from y to x. So clearly for Euclidean distance or air distance, this will hold. And then there is this triangle inequality, this transitivity rule in the distance, that the distance between x and z is smaller or equal than the distance between x and y and z. So imagine if we have a triangle, then the distance between 2 points is always smaller than the distance of the 2 edges, which are summed up together, which are forming the alternative paths, if you like, between x and z through y edge. So this distance in sum will be larger than this distance. And if any of these conditions are violated, then we do not call that measure being a metric. So in this case, we do have metric which for any of these Minkowski distance generalization, which is larger or equal to 1. So everything what is smaller than 1 for the exponent, it will violate one of these metric conditions. Here we can see various distance measures for the example of these points. So which of these points seem to be the closest to each other? I would say that the closest seem to be, to me, point 2 and 3, and the other ones are more distant. So if for the L1 norm, if we look, then 2 and 3 are distant of 2, but also 3 and 4 have distance of 2. So this is in the case of the Manhattan distance. This is the same distance as this distance, because we need to go sort of around the corner. In this type of distance measure. In case of a Euclidean distance, we can see that this distance should be the shortest one, which is here named 1.4, but we can see that this matrices, this distance matrix is actually a symmetric matrix. So we are seeing that the symmetry property is also fulfilled for the L1 norm here, and that the distance between the points themselves is 0. So that's another condition which is fulfilled, and they are also positive, which is fulfilled. And then we can check also transitivity or the triangle inequality, but we will see that this triangle inequality will hold also in this case. For example, let's have a look at these 3 points. So if we go between P2 and P3 and P4, so P2 and P4 will be the distance here of in total 1, 2, 3, 4, and for the sum will be 1, 2, and 1, 2. So it is equal the distance in this case. In this case of the Euclidean distance, L2 norm, we can see that this will be for sure shorter than this distance plus this distance. And then we have also this L supremum or L infinity norm, where we can see that, for example, where the triangle inequality will also hold. So for example, here we have the P2 and P4 is the distance of 3, and the P1 and P2 and P3 is distance of distance of 1, and then P3 and P4 and is distance of 2. So 1 plus 2 1 plus 2 is smaller or equal than 3, so this inequality also is held in this anecdotal case and in general as well. So here are the various distance measures which could be then mapped into the dissimilarity by normalizing it from 0 to 1, and then it could be mapped to similarity measure. But not all of the similarity measures, or actually distance measures, can be satisfy the triangle inequality or the symmetry. So examples are similarity measures that will be applied on, for example, measures between sets. Imagine that we have a set A, which contains the elements 1, 2, 3, 4, and the set B, which contains the elements 2, 3, 4. And then if we have these two different sets, then if we want to perform the difference between these two sets, A minus B will be 1, and B minus A will be an empty set. So then and if our distance measure is the size difference between A minus B, then this is not symmetric to size B minus A, and therefore this will be a non-symmetric measure and doesn't also satisfy the triangle inequality. So therefore, in order to satisfy these properties, we can fix that. We can change the distance measure somehow, and for example, a useful change of this measure could be that the distance between A and B will be the size A minus B plus size B minus A. This will be measuring as the distance, and this type of measure will satisfy the metric properties. Another case where we do not have the similarity condition fulfilled is the time distance. Imagine that we have a distance between 1 p.m. and 2 p.m. and we can say that clearly that distance is just 1 hour. But if we say at the distance between 2 p.m. and 1 p.m. and we are thinking in a chronological way, we would say that the distance is 23 hours. We can see this function here. If the t1 is smaller than the t2, then it's t2 minus t1. Otherwise, we will have 24 plus t2 minus t1. So this will be a negative number, which is then subtracted from 24, and that in this case give us the value 23. So we can see that this distance measure is not symmetric. And For the time, we would, if we need to have metric distance, we would need to deal with this symmetry somehow, and it might be possible in some context, but in some application context, this might not be possible. So far, we have been discussing the measures of distance, which kind of map to the dissimilarity, although the distance will be not normalized as dissimilarity should be, but they somehow can be mapped to each other. And in those cases, we have seen that sometimes the dissimilarity or the distance can fulfill these metric properties or not. And in the case of similarity measures, like proximity measures, which we will be discussing shortly, we can see that they typically satisfy the positivity property and also the symmetry property. So the similarity measures will typically have the measure will be equal or greater than 0, and these two properties are the symmetry properties fulfilled as well. We will be talking about similarity measures that can be converted to metric distance, like, for example, the cosine similarity or the Jacquard similarity or proximity measure. In case we have a similarity measure, for example, we can build some confusion matrix as well from an experiment. So we can build an experimental proximity or similarity measure where we could, for example, define in an experiment, for example, comparing perception of 0 and small o, how often it is by people perceived correctly and incorrectly, in such a way that we build the so-called confusion matrix. So in the confusion matrix here, if the 0 is actually 0 and is perceived by 0, it could be a case of 160 observers, but for 40 observers, the 0 will be actually interpreted as O. And then, in case the stimulus is actually O, but it is perceived by 30 participants as 0 instead, erroneously, but correctly by 170 participants. So we can see that there is no symmetry here. They are similar, but not completely similar. And that could be fixed, for example, here by having the similarity measure slightly adjusted based on these observations so that we have a symmetric property. And that could be done by taking one similarity of x with respect to y and similarity of y with respect to x, and then divided by 2, and then this will be then therefore automatically an symmetric measure. So this is how we can make the measure symmetric and to become a metric. Then let's have a look at various proximity measures, and we will start with proximity measures for binary variables. So if we have binary data, then we want to measure what is the proximity of this code. So we have, imagine we have two binary codes, and we want to find out how similar these two binary codes are to each other. So what we could do is, for example, we can measure that the times when both of these attributes the attributes have zeros. So if xi is 0 and yi is 0, then this will be summed up in the counts, which is this value of f00. f01 will be if x object of attribute I is equal to 0, while the same attribute column of another object y is equal to 1. So this will be count for those number of attributes. And then we have the count of a number of attributes where it will hold that we have for the same attribute 1 for x, and for y we have 0. So this will be f10, and f11 will be when the two variable, the two objects will agree on the attributes where there will be both 1, 1. And if we have these two all put together, then we can create a simple matching coefficient, the SMC, which will be calculating the ratio between how many occurrences overall are there of the attributes. And so the kind of pairwise comparisons of all attributes, and then we will choose where did they agree, so where the both were 0 and or where both of the attributes for these two different objects were 1. And this will give us some kind of similarity measure. Imagine that they always agree, then the outcome will be the numerator and the denominator will be both equal to the same value, and therefore the outcome will be 1. And if they will never agree, then it will be equal to 0. So this is the proximity measure for binary variables, and we can use it for calculating how two binary codes are close to each other, how similar they are. Let's have a look at a slightly different measure, and this is the so-called Jaccard coefficient, and it's very useful for asymmetric binary attributes, for example, for transaction matrix, where we have a lot of entries are actually equal to 0. So in order to deal with that, we will slightly modify this SMC measure of proximity so that we will ignore a lot of values which are in both cases 0. So we can see it here, for example, where we only agree when the both have 1, and we divide it by the ratio of wherever there is at least one value is non-zero. So here the ratio is slightly different to the SMC for the Jaccard coefficient in a way that it ignores the F00 both in the numerator and also in the denominator. We can see what does this imply in case of comparing two objects, like here, where we can see that there is has been a lot of shopping going on, but somebody just bought this entry element, maybe a bread, while somebody bought a soap and also bought some kind of paper towels also. So what is the similarity between these two transactions? And if these are two items items of very different kind, naturally we would expect that if there is no overlap in ones, then it is kind of there is no similarity. And indeed, we can see that for SMC, we are basically having how many times is there a overlap F11. This is 0 times, but F00 is actually 7 times. And when they are kind of disagreeing is 1 time here and 2 times here, which makes it in total 10, and this is then therefore 7 divided by 10 is 0.7 is the similarity index, because these zeros are often very similar. However, in case of the representation, if this would be just shopping cart of a bread, and this will be the shopping cart of the paper napkins and shampoo, I think I said a shower gel, then there is no similarity, and the Jaccard coefficient will pick that, because here is only 0, because F11 was 0, and F10 was 1, and F01 was 2, and therefore 0 divided by 3 is equal to 0. So the Jaccard coefficient will be for this transaction matrix a more useful proximity measure. Then we have another proximity measure, which is very popular, especially in the context of comparing documents where we have the binary variable used for the occurrence of words. Or actually, it doesn't need to be binary variable. It could be also a frequency in the sense of how many times does that word appear in a particular document. So in this case, the cosine similarity is basically just performing just a regular dot product which is between two numerical codes. So imagine that we have an X, which is a characterizing document of some words in the occurrence, how many words are of a certain kind there, and this is X and this is Y, and we simply calculate between these two vectors, if we can consider them as vectors, a dot product. And this dot product will give us a value 5, because 3 times 1 is 3, and then 2 times 1 is 2, together it will be 5, and then we will also measure what is the magnitude. So we will simply perform a Euclidean type of distance calculating of the magnitude, and then we multiply these two magnitudes together, which will be in total equal to, and perform square root of this when calculating the magnitude for each individually. And then after we multiply them together, the value is approximately 14.51, and that will lead to a cosine similarity between these two characterizations of documents to 0.31. If we will have the same code as in X and Y, or there will be somehow scaled version of one of the other, we can have easily an representation of one, so that they will be identical, or we can also find out that if they will be totally different, so always where there is a 0 in one, there will be a non-zero value, so but in total this dot product will equal to 0, then they will be completely dissimilar. So similarity measure equals to 1 for identical vectors and 0 for entirely different ones. So this is a very good proximity measure, especially in the context of document analysis. Finally, we will extend the Jacquard coefficient similarity measure or proximity measure that can be used for document data and for the frequency data. Here, where we have again the dot product, but here we have the magnitude squared, so we do not need to have the square root, and we have here this dot product again, and this measure is more efficient to calculate than the one which involves square root, and it's the extend Jacquard similarity. And in the case of binary values, this will actually degrade to a regular Jacquard coefficient. But this extended Jacquard coefficient is meant for non-binary valued vectors, similarly to the cosine similarity. Next, we will be discussing the correlation as a way of assessing the proximity of two different objects. So, for example, we can see how Pearson's correlation coefficient can be used for that purpose. However, we need to point out that the outcome of the Pearson's correlation coefficient will be between -1 and 1, and therefore it is unclear how that maps to similarity, because at 0 this means that the two objects are not correlated, or objects, or it could be also attributes depending on what we are starting off a correlation of. But in case of 1, it will be that they are fully correlated. But what is, as I mentioned before, with the negative value? If something is highly negatively correlated, is it similar or not? In some contexts, yes, and in some contexts, this will not be the case. So this will need to be treated as in the case-by-case basis. So now we will, for the first time, define how this correlation is calculated. First, the correlation is calculated as a covariance between two objects, or vectors, if you like, and then divided by the individual standard deviation for one vector and for the other vector. So in these vectors we have certain values, and they are having some kind of spread of values, and that will be measured by the standard deviation, and then this covariance is measuring the difference between the deviations together. We will see that on the formulas which we have here. So let's have a look first at the simplest part, which will be calculating the so-called sample mean, which is here, and it is simply an average of the values in case of our object, of its attributes, or across an attribute of the various values that attributes has for different measurements, for different maybe persons, if it's a data matrix about people. And that is for the one object, or and here is for another object, which is the mean for this another vector. So now we have the means for these two vectors, and we can calculate the variance. And you can see that we are here calculating the squared difference between the mean and the actual attribute value, or within the attributes of belonging to one person. If we go across the person vector, and then this is squared, summed up, divided by n-1 of the elements in that vector, and then square root of that value will give us the standard deviation. If we will not square it, then it will define as the variance value. Now we can calculate it for the first data object, and then for the second data object, and we will have the standard deviations calculated. Now observe that the standard deviations, they are somewhat similar to our covariance here, where we are calculating similarly the sum, which is then normalized by n-1 of the where the n is the number of elements in that particular vector, and then we have the difference to the mean with respect to the one data object, and the difference to mean multi-product of that to another object, and that is then summed up. And that will give us the covariance value, which we also denote as Sxy, and this value will then be divided by the individual standard deviations, and this will give us the value for the correlation. So this correlation can then be calculated for each data object, or it could be calculated across data objects for each attribute, and then compare the different attributes with each other with this correlation, Pearson's correlation coefficient. We can see how this will then look like for different values of the Pearson's coefficient. We have here a plot where the one data object or data attribute is compared with the other one, and here we can see that they are forming a very linear relationship here where we will say that they are highly negatively correlated with the Pearson's coefficient -1, and then we can see various versions where this correlation will become less and less until here in this case we have a zero correlation, and then we are again increasing to a highly linear relationship. So the correlation is studying a linear relationship of the two variables. But for example, we can see that for these two variables, it will give us the correlation -1, because we can see that one vector is simply a multiplication of the other one. If we multiply this vector by -3, we will obtain the vector x. The correlation is therefore -1, and for another case here, when we have these two vectors, if we multiply the y by 3, we will have the vector x, so the correlation will be 1. It's a perfect linear relationship. Sometimes we might have imagined that we have this vector, and then we will have a vector which will be like maybe a 9 and then 36, 0, 9, 36, which will be like a x squared, if you like, then the correlation between such vectors will actually not have a linear relationship, and therefore the correlation will definitely not be 1. So it is unclear to me. I didn't calculate what the correlation will be, but the correlation will likely be something between 0 and 1, but definitely it will not be 1, as we will not have a linear relationship, but actually a quadratic one. Finally, we will discuss the proximity measure, which is related to the Mahalanobis distance. This distance measure is calculated between two let's say, objects or vectors in general, if they reside on different scales. So their standard deviations are different, and for this purpose, if we would simply compare them in a way where this will be not normalized, we will not see how well they are correlated. And in order to understand the correlation well, the actual Mahalanobis distance is, while it is a little bit more complicated, it will be telling us whether these two vectors are correlated or not, whether there is a linear relationship, despite the fact that they might have different, they might reside on different scales. So it works in a way that we have simply a difference between these two vectors, and then the same here, but transposed. And then we have here the covariance matrix, which is a matrix which is characterized by the variances of individual vectors on the diagonal, and on the other places it will be the covariance between these two vectors. So this is the covariance matrix, and here we have the covariance matrix inverted. So it is the so-called precision matrix. We can also recognize that this is actually an exponent in multivariate Gaussian, where this will be the precision matrix, exactly calculated in the same way. So we can see here that while if we are calculating, for example, these 2 points, they all somehow correspond to the same distribution, and we can see that there is quite some kind of a correlation. We see that the distance measure, if we will apply simply the Euclidean measure, it will give us the value of the distance is 14.7. However, the Mahalanobis distance will take into account the fact that while they are distant in the Euclidean space, on the other hand, they have there is a linear relationship, which this correlation will be somehow that they are correlated, and therefore we will have with the distance measure based on the Mahalanobis distance will give us a smaller value, which means that they are more similar to each other than the Euclidean measure would estimate. So with all these measures of similarity, we are now well equipped in order to compare various values within our data, depending on whether this data is ordinal or nominal or interval or ratio based, and whether these various attributes or data objects are residing on different scales or not. And based on that, we have various ways how we can compare them. With this, I would conclude the chapter or lecture on data mining introduction and the characterization of data. And I'm looking forward to meet you at the next lecture.